Hello, hello. Hey, Ryan. A little bit early today. Hey, Bob.
Hey, man.
How you doing? Good to see
Good.
you.
Yeah. Getting back in the saddle.
Yeah, cool. Good stuff.
Yeah. Quite a few more users than a year ago, man.
Oh, yeah, for sure. It's up now. I was looking at it this morning. 3,044 people have joined since the beginning of it. So it's yeah, a lot of people obviously want to learn and want to get into this. Uh, yeah, which is great. We need more. You
Yeah,
know,
it's
we don't have
fantastic.
enough. Yeah, we don't have enough people. So
I think one of the things that's been really valuable in this coming from like an app development background has just been like expanding in my mind like what the mental models are on how to approach these problems. So that's
yeah,
maybe one of like my primary observations here is like we've talked a lot about like machine learning and models, but just how much of this actually comes down to system design, problem recognition,
right.
decomposition there. And so I think that's why, coming through the first round, remember earlier on you said, hey, if you get 10% now, you go through the next cohort, you get 10% again. And I think that's probably been my 10% from now is it's just giving me a way to think about these problems and
Yeah.
understanding, even what I'm seeing. So I really appreciate it from that perspective.
Cool. Well, what makes me happy is that would be precisely the 10% I would want most people to get, right? And I'm sure if you go to a class taught by somebody that works in academia, somebody that's a researcher, their 10% will be completely different to mine, right? So their focus there would be different. But I'm a developer at heart. My job is to build products for people,
Sure.
regardless of whether you're using machine learning or you're using whatever. Nobody cares. People want to solve problems. So that 10% that you just mentioned there, that's the most important thing for me. Like the way you approach your problem, the way you start like with the simplest possible solution and you start building components and pieces and you start organizing your project in a way clients see progress every day, not just at the end of 6 months, but what can I get you so you can start seeing value after the first week. And then after the second week, we make it a little bit better. Like that mentality, that's one of the most valuable things, I think, for an engineer out there. So I'm glad that that's some of what you're getting. Uh, yeah, like you said, there is a ton of content and it's a ton of stuff here. Okay. And it's impossible that anyone can get or can cram all of these in 3 weeks. That's not just a thing. Okay. If that's what you want, just go and take a $99 Udacity course. That's gonna tell you, hold your hand and tell you do this, do this, do this, and you're done and you feel like you learned something and you completed the assignment, right? That's not the goal here. The goal for me is just to show you where the doors are. That's usually the analogy that I use in my head.
Sure.
So you know that there are doors, and when you have to cross to that room, you know where they are and you know where to investigate, right? I read a lot and I use maybe less than 1% of what I read. But I read not because I want to learn how to do things. I read because I want to know what the possibilities are. So tomorrow, when there is potential for me to do something, oh, I think I saw a solution for that. I think that's possible. Let me just go back and, you know what I'm saying? That's sort of like my goal here.
Maybe another way to say it is like reduce the size of the black box. I'm sure there's still a lot of black boxes out there to people, but it went from this giant black box to, okay, now it's a little bit smaller. I can see with some of the colored boxes, right? We've turned some of these opaque. And
yeah, no,
Thank
100%. And obviously you have access to all of the future cohorts. They're gonna keep improving. I'm gonna keep adding things. One of the things that I'm working on right now is increasing the code walkthroughs with code related to agents and MCP and A2A. I have plenty of examples for all of that, but I cannot just throw all of those examples there because I need some sort of like thread connecting them, right? I need some sort of, I need to organize them for a class. So my goal is to get first into some rack examples using the same documentation of the code walkthroughs, a little bit meta there. We have all of these code walkthroughs which are written, it's just text. So I want to create a rack system that uses that as the knowledge base to answer questions about all of this documentation. So that's what's going to be the rack example, and then turn that into an agent, and then introduce MCPs so we can access tools, and then create other agents, and then connect agents together using A2A. That's sort of like the goal, what I have in my mind, and I'm working towards it. So you guys get access to all of that code. We're going to talk about MCP and A2A and agents in the next session. On Thursday. Yeah, so that's sort of like the goal. So hopefully it's going to keep getting better. Cool stuff. So today, what are we going to be talking about today? Let me share my screen. Okay, so today we're going to be talking about the real challenge of all of this shit that we've been. By the way, somebody told me on Twitter, you might be listening to this. Somebody said on Twitter that you were listening one of my classes and you had your 7-year-old next to you, and I was coursing. And unfortunately for you, you had headphones, so he or she did not hear me say, a course word. I apologize. It's just who I am. So I don't have an HR department, so nobody's sort of like, telling me what to say and what not to say. So I apologize about that. But yeah, wear headphones just in case, or don't be around kids just in case. So yeah, we spent a ton of time talking about building models and deploying models and whatnot. And this is something funny, because I usually use books because, like, as a reference point, and to illustrate the difference between theory and practice, right? So the machine learning books tend to stop at some point. Like, they tend to stop when you train a model and you're done with it, and life is beautiful because you just deploy this model. By the way, most books don't even talk about deployment. They talk about, oh, it's high accuracy model, we're done, we're just happy. And that's actually when the work starts. That's not where the work ends. You're not done. It's actually, your entire, all of the problems are right in front of you at that point, right? So I have here, I've showed to other students. Actually, I have it here. It's very easy to show. I have this here. I've shown other people as well. I don't know if any of you recognize what this is. Some of you are too young, I can tell. Some of you are, you guys are like me, 40 something. You guys use this. This is a 5 1/4 floppy disk, and it's fluffy like this, a floppy disk. Yes. This, on a good day, was able to store 420 kilobytes of data. They came out of the factory for 360 kilobytes of data. But then there was a way to format them so they could store 420. And I learned to write software using one of these. I had like a bunch of them. One of them was for the operating system. This one literally says top secret. I wrote it and I signed it. Top secret. I was 14 at the time. I have no idea what's in this one here. But my point in showing you this is that I was lucky enough some time ago to find somebody who collects all hardware, vintage hardware, and he has a computer with a reader for this, and I was able to read one of the discs that I have, and I got a game that I wrote when I was 14. No, actually, I was not 14. I'm sorry. I was 16 to 17 years old when I wrote the game. It was a very popular game at my school. Everyone played it. I left my school and I came back visiting, and everyone was talking about this freaking game. I'm like, that I built it, but well, it was super fun. Anyway, I was a nerd. So yeah, I was able to get that game out of this. We're talking about a 30-year-old game, a .exe file, and I was able to run it on a Windows computer. No changes. I mean, just the exe file, I was able to run it, and it ran. And that is something that a machine learning model is not going to do anytime soon. So obviously, you create software, and just removing the idea that hardware obviously changes and all of that good stuff. The software, the way you build it, is just going to stay the same way going forward, right? A calculator that you built in the 90s is still going to be a calculator today and function the same way, because it's basically following rules, and the rules are just going to be the rules. Machine learning does not work like that, right? Machine learning makes predictions, but the world changes. And when the world changes, the machine learning model will continue making predictions. It just happens that all of those predictions are going to be wrong, right? So the problem for a machine learning engineer, for somebody that's working with these models, is we need to keep making, it's like a cat and mouse game, right? Because the world will continue changing, and you have to keep adapting and updating your models if you want to catch up. And we're going to see multiple examples about that. I'm going to start the easy way and try to complicate it a little bit going forward. But the most common way that these models are going to fail is because of edge cases. And probably 99% of people who are listening to this right now know what an edge case is. I don't know. Imagine that you are building a self-driving system, and all of a sudden you get somebody riding a bicycle on a highway. You're not supposed to do that. That's not something that I've never seen it myself driving. Never seen that. That's an edge case. So if you do not train your models with that edge case, you have no idea how the car is going to react, the self-driving system. How is it going to react to something that has never happened? Or I don't know. I was going to say an alligator crossing the street, but no, that's not an edge case. Definitely not here in Florida. That happens all the time. I've seen it. So yeah, that's what an edge case is. Notice that an edge case and an outlier are two different things, although some people treat them interchangeably. An outlier is like a sample that's out of distribution, like it looks different to everyone, to everything else. An outlier does not necessarily it's gonna cause a problem. So it's not necessarily a problem. Might be an outlier, but might not be problematic. An edge case is something that causes a problem, right? It causes your system to fail, and you are going to have to deal with that. And unfortunately, edge cases are inevitable. You cannot do anything to prevent them from happening, right? You can prepare your system to respond to edge cases. You cannot prevent the edge cases from happening. A conversation I usually have with people in these classes, whenever we get into the topic of splitting the test set from the train set, there is always a discussion about that. People are not used to that conversation. And there is always somebody who's smart who says, but wait a second, what happens if you split your test set from your training set? And just by dumb luck, it have one of the categories happens to be on the test set, you don't have it on the train set. And if imagine that you have, like, I don't know, like a column that talks about animals, and you get cat and horses and dogs and whatever, elephants in that category. But when you do the split, there's only one giraffe, and that giraffe goes to the test set. So if you split before transforming, now you're going to train a model that has never seen a giraffe or doesn't have any examples about giraffes, because that was on the test set. And they are sort of right. But their solution they usually propose is, no, you have to look at the whole data set, so you don't leave the giraffe out. Well, what happens with the armadillo? What happens to the alligator? They're not part of the train or the test set. So yeah, you might cheat in order to incorporate that giraffe from the test set, but what are you going to do with all of the animals that are out there that are not part of your data set at all? You have to prepare your system for those as well. So you might as well not cheat and use the data from the test set, and instead focus on preparing your system to handle the unknowns, because the unknowns are going to happen. They are inevitable. Does that make sense? You have to design these systems for edge cases. They have to be prepared. If your system fails when it sees a case out of distribution, you build a piece of crap. That's it. Okay, so you have to prepare for that. Any questions so far? Good. All right, so let's talk about the second category here of mistakes, or not mistakes, of things that are going to make your system fail. They're called feedback loops, and everyone has a different name for these feedback loops. Some people call them positive feedback loops. I like to call them positive feedback loops. Some people call them degenerate feedback loops. Some people even call them negative feedback loops. And it's just the same thing, just a feedback loop, okay? The analogy for these ones here that I use are bank runs. Can anybody tell everyone else what a bank run is? Go ahead, whoever, okay. Yeah, Kevin. Kevin, sorry.
Yeah, it's I guess when people are worried about there not being enough money in the bank, so people go to the bank to take out all their money, which sort of makes the sort of a self-fulfilling prophecy.
That is the word that I was looking for. It's kind of like a self-fulfilling prophecy type of thing, right? So, somebody says, hey, I think the bank is going to run out of money, and it's just a lie. But then people start believing it. And what they do is, holy shit, I have to get out my money before they freeze the bank. And everyone starts getting out their money, which causes the bank to fail. And that's what a bank run is. So I think about feedback loops kind of the same way. They're sort of like a self-fulfilling prophecy. So let me give you a couple of examples here, so you can see how dangerous these things are. Okay, so this is a very, very simple example. I'm going to complicate it a bit in the next few examples. But imagine like the New York Times. If you've read the New York Times, they have a section in the New York Times with bestseller recommendations, okay, where they publish let's say the top 100 books, the best sellers, okay? So they make it into the list because they sell a lot of copies. That's why it makes them best sellers. But the New York Times, imagine they have a model that's gonna decide who goes into the list, and they publish the list. And what do you think the list does? Who can tell me what's gonna happen here? New York Times publishes the top 100 bestsellers. Mark?
Yeah, so it probably, if they publish that top 100 list based on sales, then that reinforces the loop that those top 100 are going to generate more sales.
Sell more.
They make them
Yeah,
more
they're
popular.
going to sell even more. Exactly.
So that's going to feed back into the model. The model is going to look at that and say, oh, I guess these top 100 are selling more than anyone else. So that will be in the next week and the next week and the next week. And it's just, it's self-fulfilling prophecy type of thing where it's getting reinforced by the fact that you publish that list, you dummy. And by you publishing the list, you're making the books more popular. Therefore, that's going to continue happening. Think about Spotify with the top 100 pop songs. Well, people who wants to listen to pop, they go to that list and they will continue listening to the songs on that list, which will make those songs more popular, which is the key factor for them to make it into the list again. That's when you get it into one of these lists, it's really, really hard for you to come out of these lists. Really, really hard for you to come out because it's just everything is acting in your favor. It's like a positive spiral. Mark?
This can be very direct or very indirect, right?
Yes.
The model here could just evaluate the internet, what are the most written books, and find its own list.
Mm-hmm.
This would be direct, but it's also can be very subtle or what's the English word? Very hidden network of dependencies that create such a loop.
Yes, that is correct, and that's what makes feedback loops really, really hard to detect. I'm going to show you a couple examples how that subtlety happens and how difficult it is to just detect that. This is a very obvious case. And by the way, just so you guys know, I do not know what the New York Times does to break this feedback loop. I'm sure they do something. I also know, because I've read authors that talk about the bestsellers, that once you make it, it's very hard to get knocked down. So I also know that, right? So again, I'm not sure about the New York Times, what they do. I am sure what Spotify does. I mean, not technically specifically, I am sure Spotify does the right thing to break the cycle, but we'll get that in just a second. Here is another example, okay? This is something that happens even regardless of whether you're using machine learning model or not. Imagine just the police department of a city, they have a crime model, okay? And that crime model is designed to predict where crime is going to happen, okay? So let's imagine that crime in this case are just traffic violations, okay? So the police department predicts where traffic violations will happen. So they can actually distribute across the city the police force. They want more policemen and policewomen close to the places where traffic violations are going to happen. Okay? So what do you think is going to happen here? Mark?
Well, if you place your policeman at a certain point, the probability increases that they will spot a crime. Because if there is no police, then they won't spot a crime. So you generate your hotspots in the statistics automatically.
That is exactly what happens. So the places with more police presence are going to be the places that will report more crime, thus justifying even more police presence there. So this happens across all of our neighborhood, across the world. You get certain areas that are hotspots for crime. Therefore, there are going to be more police people there. That they're going to continue, more crime will continue to happen there just because there are more people to report it, to spot it. In my community, I live in a community that's very safe. There are teenagers, just like in any other part of the world, and teenagers are freaking crazy and they do stupid shit. But when they go and steal a car in my community, parents don't report the crime. They just talk to each other and they solve it. No crime reported. If you live in a community that is not like mine, oh, you are getting reported. So that inflates the number of crime coming from certain areas versus the other areas. If you have a model, if you are the one building this crime model and you don't take that into account, your model is just going to be crap. It's just going to be predicting something that is not real. Okay. Here is one that is a little bit more subtle. Okay. This is a churn model. For those of you who don't know what churn means, this is the term that companies use to talk about subscribers that leave, that subscribers that stop paying. So if you have a subscription-based service, people who stop paying, who quit, they cancel their services, they are churning. Okay. So it's very, very useful for these companies to have churn models, because with a churn model, they can predict who's going to leave and maybe offer incentives to that person so that person stays. So very, very helpful. Anyone with subscription services wants a churn model. So here is an example. So imagine that, this company, they built this churn model, and the churn model predicts that John Doe, Jen Y, Mary, Bill, and Sue are going to churn. Okay? So that's the list of predicted churn. And then the company gives these to the sales team. They tell the sales team, hey, listen, all of these people, we think they are going to stop paying. Do something. The sales team prepares emails and sends all of these emails to these people. And at the end of the month, when the month actually ends, only Jane and Bill churn. Everyone else stays. Probably thanks to the sales team. They offer, rewards and whatever. And then we get the actual churn, and obviously that becomes the ground truth data for our model. Our model made a prediction, but there is actually a ground truth data, which is the people who actually churn. And we retrain our model and we start the cycle all over again for the next month. What is the problem that you see here? Anyone else other than Mark? Do you see a problem here? Is there a thing that we need to fix here? No, Mark?
I would guess the ground truth is modified to have the hardest to convince people, and all the people who get easy targets will be dropped out of the model, so you lose on the ones that you can affect best.
Mm-hmm. You are onto something. Dejan?
Hi. I think what's missing here is the reason how they, or the method how they persuaded the customers to stay. Could that be a feature that might be added to the prediction?
That's an idea. Caleb?
Yeah, maybe this is what he meant, but yeah, the sales team stuff needs to be included in the model.
Mm-hmm.
And yeah, so it's just not a good model for that reason.
Right. Vishwanath?
So if the people leave and then the model uses those people data, as ground truth, if those people aren't really there at all, then the ground truth becomes useless because those people aren't really available.
Right. So the problem here is that it's not fair to tell the model that the actual ground truth are the people who did not churn when something else acted on the original list. So the model made a prediction that 1, 2, 3, 4, 5 people were going to leave. But then somebody cheated, somebody acted on that prediction, and now only 2 people left. Maybe if the sales team was not involved, maybe only Jane and Bill would have churned, but we don't know that already. Like at this point, we don't know that because the sales team offered incentives. Therefore, they messed up with the reality of that model. The model does not know that the sales team is going to act upon that. So if you put this data into the model again, the model is going to say, oh, I guess I made a mistake. Whatever patterns I learned to predict that John, Mary, and Sue were going to churn, I was wrong. Therefore, I'm going to readjust because those people shouldn't have churned. That is you're just sending a bad signal to the model. So how do you solve this? Okay. You guys already told me an idea, and I'm going to give you my opinion on that idea, but that is an idea nonetheless, which is we have to incorporate what the sales team does as part of this training process. The data set should include the sales team incentive, so the model learns that after an incentive, well, there might be something else going on here. That's an idea. Anyone else with a different idea, maybe a simpler one? Caleb?
I think you just have to change your model to be something to predict something that isn't that end result. So you can't use actual churn. You need to find something that can't be acted on. That's an idea.
Yes, I just don't know what that means specifically, but yes, that could be something that we explore. I mean, you know the path. I just don't know what the solution is, but you definitely know the path. We have to avoid that cycle here, weird cycle here. Guillermo?
You let them churn, in quotes, like, but then offer an incentive, but after you've confirmed that they were going to churn.
That's an interesting idea. I think that will work, technically speaking. I don't think it will be great for the business from the point of view of after somebody like cancels and whatnot, it's going to be hard to bring them back. Like they already made up their mind. I might be wrong. This might be use case dependent. Like for certain services, it's going to be easier than others, but that will work. Yes. So basically what you're doing is you don't act upon the information that the model gives you until after it happens. So you don't do anything there. Anyone else with a different idea? Julian?
You can not treat the model about churning, but about maintaining the relationship with the client. So churn is not going to happen because you maintain a good relationship with your client. So you know the data points where I don't know, maybe it could be asking them about how happy are them about the service or product, but you maintain the relationship.
Okay, I see what you're saying. So that will solve the problem, I think, but then you will lose the possibility of acting upon the churn, right?
Yeah.
Like if you don't know if somebody's gonna churn, if you make the model about something else, which is the client happy or is not happy? Like how do you know the client is not happy?
Because you ask them a question like, from 1 to 10, how happy are you about our service?
Right.
And,
No.
Yeah.
But sorry.
But you can maybe you can have the probability if they're not happy, they're gonna churn. So you can.
Right. But then when you know that when you predict they are going to churn, let's say you compute that probability, now you know they're going to churn, or you think they are going to churn. The question is, what do you do with that information? Are you going to act upon it? And if you do, then how do you put that feedback into your system so the system gets better over time? Make sense?
Yeah.
Mark Smith.
So I would say yes, you act upon it, but why not put in your data set, like have some sort of feature that's like the time in which you intervened or acted upon it, and basically look to capture that in the model. So like, the first time you would have done it, prior to that, everything would have been essentially zeroed out, but
Right.
you're then capturing that signal going forward.
I think this is similar to the idea that Caleb proposed. Like you have to incorporate, or one solution is incorporating the information that the sales team acted. And if you incorporate that information, somehow the model will take that into account the next time. Okay, so one more. Then there is a simpler solution. Somebody hinted at it in the chat. There is a simpler solution to all of this. Okay, Mark Alexander, go ahead. No, you're muted.
Take 10% of the people predicted to join and not let the sales team acting on that and use that data. Then you have the truth, or 10% or any percent that the business case allows, and use those where the teams have not, the sales team has not acted on to make your predictions.
Yeah,
and make it your ground truth.
The solution that you could possibly make here. So let's say I have 1,000 customers and I predict that, I don't know, 100 of them are going to leave. So what I'm going to do is I'm going to set aside a 10% of that 100%. And the numbers here, you have to pick what numbers make sense to you. But let's say out of 100 people, I'm going to take 10 of them and I'm not going to do anything with them. Okay? I'm just going to let them churn or stay. So that will be the ground truth that will make it back into the model. And then I'm going to let the sales team go crazy with the other 80 or 90. Does that make sense? So basically, I'm keeping a portion of my data untouched so I can feed back into the model and make that model better. I'm trading off some of the amount of data by having quality values that I can feed back into the model, like a control group. That's actually the answer. That's very simple to do. Adding a new feature that to model the intervention of the sales team is possible. It's way more work, because to model how, like now the model has to take into account another feature. What happens when we add new dimensions to a data set? Well, everything gets exponentially more complex for a model. Remember, there is something that's called the course of dimensionality that talks about this. The more dimensions you add to a data set, the more complex it is for a model to just produce good results. You need way more data, exponentially more data. So just keep it simple. Take a percentage of the people and you never tell the sales team about those. You act upon 1%, you keep the other percentage as a control group. Again, the numbers vary here. You can do half and half, you can do 80 and 20, you can do 20 and 80. Doesn't matter. Okay, so hopefully that makes sense. Point being, detecting feedback loops is not easy. Detecting that these things happen is not obvious to everyone. Okay, especially when predictions make the world change. Okay, so one example that I like to tell people is here, imagine you have like a bear population or an alligator population that are coming out in the middle of a city and eating people's pets. That happens here in Florida, okay? So an alligator comes out, eats your dog, bye-bye, is the whatever it is. Then the city decides, you know what, we can predict where alligators are going to come out. We know their patterns, we know their hiding spots, we know their seasons, so let's create a machine learning model that predicts where an alligator is going to come out. So you can don't leave food outside, put your pets inside your house so you can protect. And they release this model on a beautiful government-created website, and people start checking out the website so they know when to act. And people start acting on that model, which is very good. And alligators come out and there's nothing to eat. What do you think is going to happen after only one season? Alligators will adapt because they came out using the regular patterns and they did not find any food. So they will adapt. Darwin tells us that adapt or die. So because of the success of that model, the world will change, making the model useless over time. Does that make sense? Because the model is successful, because the model makes good predictions, alligators, the world, will adapt and they will start looking for new spots. They will start showing up where the model does not say they're going to be showing up, making the predictions of the model obsolete very, very quick. Okay, that is the problem that we're dealing here. How do we fix that problem? Well, number one, we need to monitor the models. We need to understand what this is happening. And number two, usually retraining our model. We have to constantly update our models. Okay, somebody's saying data drift. Precisely, that's what we call it. We call it, like people who write books, they call these distribution shifts, right? So think of it, the word distribution, just so I don't get too technical. Distribution is like the shape of the data. Where is that data coming from, right? Like the values. If I have a random number generator between 0 and 10, I generated a billion values between 0 and 10. You know exactly what the shape will be, okay? It will be random between 0 and 10. That's sort of like the distribution of my data. And a distribution shift is when those values, you're expecting values between 0 and 10, and all of a sudden the values start shifting. Now you're getting values between 1 and 11, or maybe 2 and 20. And when that distribution shift happens, your model stops being successful. Okay, now there are multiple distribution shifts. First of all, like the canonical example is this one here. We only have the data we have. You're training your model with the data you have at hand. And that data is not infinite. So imagine that you're training your model with the blue dots. That's what you see. That's what you have access to. And your model, a good model for the blue dots, it's that black line that you see there, right? That would be a good model that represents that distribution. But just happens that you don't have access to the gray data points. You just don't have the gray data points. You don't have access to them because that data is produced by different sensors, by different processes in different countries, using different languages, whatever. So you don't have access to the gray data points. Therefore, your model is not going to model that distribution correctly as soon as it's exposed to those data points. Does that make sense? This is what a distribution shift looks like, right? You build a model for the blue data points, you deploy your model for the gray data points, your model is just a piece of shit. It's not gonna work well because they never had access to the gray data points. Now, why does this happen? Well, number one is because you're doing that. You're just deploying your model somewhere else. Number two, because you have a bug. Let's say you just built, everything is perfect, everything is beautiful, and all of a sudden, Mary Jane, she's working on the pre-processing pipeline. She commented out one line she shouldn't have, and that line was the one standardizing a column. And now all of a sudden, all of those values that before were between 0 and 1 because they were standardized, or not between -1 and 1, just small values around 0, they were standardized. Now all of those values are between 0 and 10. That bug will cause a distribution shift. Your model won't be able to make as good of a prediction using those samples because there was a bug in your pipeline, okay? Or maybe the world changed. Maybe somebody replaced the old video camera with a new version of the video camera. That happened to me all the time. And therefore, the data that you're receiving is different. Same images, just a different quality, a different pixel density, a different lighting on those images. And now your model that's used to treat images certain way, now it sees a new image with a lot of luminosity, and the model is like, I don't know, this is a giraffe. And no, we're talking about cars here. So all of those are reasons for distribution shifts to happen. And these distribution shifts can happen in many, many different shapes and forms and times. Like the first one here is what we call a sudden drift, right? When your model is working, everything is beautiful. Those are the blue dots right here. And all of a sudden, boom, the data completely changes. overnight, the data completely changes. This is like COVID. Just overnight, the world went to shit, right? You know, the factory producing toilet paper, on Thursday, they were predicting that we're going to sell the 1 million rolls of toilet paper. And on Saturday, everyone started, I don't know, wiping their asses more. And now it's not 1 million toilet papers, it's 10 billion toilet papers. That's what they are supposed to produce. Just crazy demand, right? So that happens just overnight. You get this gradual shift as well, right? The gradual shift is that you start seeing more and more different samples, okay? So just to give you one specific example about this gradual shift, I've worked a lot with consumer produced pictures, like the cell phone pictures. Every single year we get a new phone that it makes pictures better and more beautifully and more resolution and more pixel, whatever, quad pixels. And what you start getting is this gradual shift where you start receiving images coming from new cameras. At first, you get just a couple images, and then all of a sudden, you start getting 3 more images and 10% of images, and then 15% of images. And you're not even done with the new camera, and you start receiving even no images from different cameras. So you start getting all of these shifts happening gradually, right? Then you get incremental drift, right? And think about this, about people eating, you know, when we invented Coca-Cola and McDonald's, think about the weight of people in the world. And this is kind of like the gradual shift where we started stuffing our faces with Coca-Colas and McDonald's. Well, the weight of people started increasing over time. And before you had like a climate change, right? Well, I don't know, the ocean rising in level. You see that gradually over time, or the temperatures is a good example. Temperatures rising over time, slowly, but surely they are increasing. And then you get like a recurrent drift. So something that happens during a period and then it goes back to normal. It's similar to like seasonal events. And even you could consider a seasonal event like a distribution shift where everyone is buying stuff during Christmas, and then what, you know, the holidays are gone, then people start to the normal habits. So you should be thinking about all of these possibilities because they are going to happen. Okay. Now I want to touch on 3 types of shift. There are more, depending on the book that you read. These 3 are the ones that take care of, I think, of everything that matters. But again, if you read a paper, they might have another dozen of these. So the first one, the most important, or one of the most important ones, is covariate shift. I hate the word covariate. It's just freaking difficult word for me. But this occurs when the input feature, the input data that's coming into your model, changes in distribution, but the relationship between the input and the feature and the target is the same. Let me give you one example because that's a mouthful. So imagine a loan approval model. So this is a model that's going to approve loans, okay? And imagine that you take that model and you apply it now to a younger population. Okay, so the applicants, the age, the demographic of the applicants might have changed. Like before, you were using this model with an older population, or you train your model with an older population, and then you apply this to a younger population. The input data changes, but the relationship of the characteristics of the people, in order for them to get approved or denied, that does not change. Like you still have to make certain income, you still have to, you know, I don't know, own your house or live in a certain neighborhood, whatever it is. But those relationships do not change, but the input data you've never seen before, it changes because now you get a younger population. That is covariate shift, okay? That's the first one that you are going to experience. The second one is label shift. And this happens when the distribution of the target variable changes. The target variable is the prediction that you're expecting. But the relationship between the input and the target remains the same. So again, same deal, the conditions given a set of inputs for you to get a prediction, that does not change, but the distribution of those predictions change. An example here is there is COVID and all of a sudden everyone is sick. Like every patient that comes to the doctor before COVID or before the flu season, every patient that comes to the doctor, or 80% of the patients are not sick. After the flu season or during the flu season, now 80% of the patients are sick. The conditions for the model to consider you sick or healthy, they have not changed. But the number of predictions of one type completely changes comparing it to before the flu season. That is label shift, okay? And the final one is concept drift. And this is one that just pisses me off a lot because this is what the real world changing means. It's not just the input data or whatnot. It's that the rules that we learned, they're different. Okay, that is when, well, now the same conditions as before, they don't give you the same outcome as before. Like before, if you were middle class, you probably could afford like a house in a walkable neighborhood. Not anymore. You're still middle class. You're still making the average income, or I don't know, higher than the average income. But now you cannot afford the same house. That is concept drift. Okay, so one example here is a customer behavior model that was trained on past purchase trends might not longer be valid if the customer preferences evolve significantly. Like before, I was into, I don't know, one of my previous hobbies. I don't know what it was. Let's say guns. I like guns. I really enjoy guns and whatnot. And before, I used to be into guns a lot more than I am today. Amazon does not sell guns, but assuming that they do, any recommendations of guns from Amazon, it will fall flat now because I don't care that much. So my preferences change, so their model has to be updated because I don't care about those anymore. Does that make sense? Concept drift, credit card fraud pattern. Yeah, yes, when I came here to the States, thank you for mentioning that, Prashant. When I came here to the States, I remember most, or based on what I read or whatnot, most of the credit card fraud happened physically, meaning it happened when you handed your credit card to somebody else. For those of you who've never visited the United States, you are from Europe, you might have no idea what I'm talking about. In Europe, you do not hand your credit card to anyone. They bring the machine to you. So they bring the machine to you and you pay right there. Here in the States, we give the credit card away. We give it to the server, the waiter, whoever. They take it away, they come back. That's how you pay. And I knew of people, I did not know people, but I knew of people who had these little machines right here, and they were paid a lot of money for every credit card they, slid through it. So basically you have like a waitress, and she had that machine, and you handed your credit card, and she will swipe your credit card through that little machine, and that's it. You did not realize what just happened. And that little machine would clone your credit card information. So later on, they could print a new credit card with their name and using your information internally. And that's how they would steal from you. So that's one way of stealing credit card information. Right now, banks have a different challenge where credit card fraud does not happen physically anymore, or not a lot of it. It mostly happens electronically. So now the fraud happens with computers and online, and that's where what all the fraud happens. That is concept drift for that. Thanks for that. Thanks for that example. Mark, go ahead.
I'm not perfectly sure if I have understood the label drift in contrast to the distribution drift.
This one here?
Yeah.
Okay. So the label is, let me try to give you an example. Okay. Imagine that you have a model and during training, consistently, you detect that 1 out of 10 samples is fraudulent. That's what you get during training. And you take that model and you take it and you apply it to a convention of hackers. You apply that model of credit card hackers, just making credit card transactions. Well, all of a sudden, not anymore you're going to get 1 out of 10 transactions as being fraudulent. You're going to get 5 out of 10 transactions to be fraudulent, just because you are applying your model in a place where more hackers are causing problems. So
Okay,
what you-
and then my quality measures of my model might be bonkers because the label ground truth is distribution is different.
So the data, the input data, what you're seeing different here is the predictions of your model are different from what you're expecting. But the conditions, the input data is the same, has not changed. And the relationship, I mean, the patterns for you to determine if something is fraudulent or not has not changed. So they all stay the same. You're just seeing more of one type than what you were expecting.
Okay.
That's why the example here is, imagine a doctor treating patients, and during the whole year, 1 out of 100 patients is sick. So only, 1% of patients are sick. But during flu season, 10, 15, 20% of patients are sick, right? So your model is still getting the same input data about patients. Nothing has changed there. The relationship, the patterns for your model to determine if somebody is sick or not has not changed.
Got that.
You're seeing more sick people. That's label shift. Okay. Now, whether or not label shift is problematic, we don't know. That
Okay.
It depends on the use case. Make sense?
Makes sense. And for the last one, the
The last
concept
one
drift,
is
yeah, I think I understand it. Here, I just would like to know if that's also covered by something like game theory, where you have an agent on the other side who tries actively to change the rules or take your model into account while applying reality. I would
It could
expect
be,
that
yeah,
this
it
is
could be
very
like that.
strongly creating new concepts.
Yeah. So the concept drift, for example, is the alligator example that I gave you, where they changed their patterns, right? So the alligators are not waiting more. The alligators are not more aggressive. The alligators are not smarter. So the input data is the same, but the conditions, the patterns that the model learned to determine where the alligators were going to show up, those are not longer valid because alligators are behaving differently now, right? Instead of coming out during the afternoon, and that's what the model learned, now the alligators learn to come out during noontime, or during the morning, because that's when food is outside. So the patterns change, that's concept drift, right? Your model is not longer making good predictions. That's what's happening there. Lucas.
Yeah, a follow-up to that. In dealing with concept drift, does it mean you need to go find yourself new features that redo some kind of a analysis part of the data and go find new data in that order?
So I don't know. It could be, but it could be as simple as retraining your model with the new data. That's the most important thing. Whether the new data that you get is enough to make predictions, that's something I cannot tell you. That's use case dependent, okay? So the easiest solution that you can do here is, okay, my old data obviously is useless at this point. Alligators are not following the same pattern. So all of the data before that explains the old patterns, that's just crap. I don't care about that. I need new data, and I need to retrain a model with new data. Now, that new data might be enough for you to build a new model to learn the new patterns. Or you may need new features that explain the patterns, but you don't know that. You have to start by retraining and evaluating and seeing what and modeling, and we're gonna need this extra thing right before. Maybe only married alligators are the ones changing their patterns. And being married was not a feature that you were considering for alligators. And for the new version, you're going to have to consider that being married is not the alligators. You get the idea.
Yeah.
They are, I don't know, in mating season, they have a mate being married. You get the idea. So the point is, your model will stop to work. It's just gonna all of a sudden. It doesn't need to happen suddenly. It could happen like gradually. It's gonna start going down and down and down. And we're gonna talk. I think in session 6, we're gonna talk about some of the conditions or some of the triggers for you to understand when you need to retrain. Like at which point should I retrain my model? It's not that you're gonna be waiting and the next day, oh, my model is crap. Let's just retrain it. Usually, it doesn't happen like that. So we need to be proactive and determine when to retrain. We're going to talk more about that in session 6. But yeah, that would be the idea there. Yeah. Any other questions about this? All right. So let's talk about monitoring. So monitoring is what you do in order to understand what's happening. If you don't have monitoring, you have no clue of what's happening. It's that simple, right? It's that simple. And I'm sure it will become painfully obvious that this is like a truism, like, duh, of course, if you don't monitor, you don't understand. But I promise you, it's also true that many, many, many companies that have machine learning models out there, they go by vibes. They have zero understanding of what's happening, zero monitoring practices. And what I mean by vibes is usually in the form of our client called us because we're making bad predictions for them. Those are their vibes. And as long as we don't get a phone call, everything must be good. And that's just horrible, okay? So I'm going to give you a few examples of the type of stuff that you need to monitor. And monitor is fancy word, monitor. This is just paying attention to, looking at, logging information and looking at and displaying charts and whatnot. The first one is the model inputs. You need to understand whether the inputs to your model are changing. There are a myriad of ways of computing this, of mathematically determining if something is changing in your input data. In the code walkthroughs, I used a library that's called Evidently. Evidently does the math for me. I tell Evidently, this is the data that I train on. This is the data that I'm capturing in production. Please tell me what's changing. And Evidently will do the rest. Why is this important? Because if the input data is changing, is drifting, that spells trouble. That's telling me that something is going to happen down the line if it didn't happen already. If I'm watching the input data, the weight of people getting into my roller coaster, if people are getting fatter over time, my roller coaster will feel it at some point, or my planes are going to feel it at some point. I have to adapt before the plane falls from the sky, right? That's the idea. So here, you can do a bunch of stuff, like simple stuff that you can understand. But again, the recommendation is just to use a library that does this for you. Mark Smith, he added a link right there in the chat with, I think is for Evidently. Yes. Just don't do this manually. But if you want to think about this or explain it, you're going to track things like, I only support elephants, dogs, and cats in my animal feature. And if in production, I see a chicken, I should not be making a prediction. I should know that there are chickens out there and I should act accordingly. That's just a simple one. Just check that a value belongs to a predefined set. Or minimum and maximums. If the weight of people that you're used to, or the median, the average of people is, I'm sorry, I'm American, 150 pounds. Sorry, European guys with kilograms, stupid kilograms. Who weights people in kilograms? You guys are sick. 150 pounds, that's the average of people weight. Then if I start seeing that increasing over time or decreasing over time, I should pay attention to this. So all of these simple computations you can do very, very easily. This is sort of like a diagram of the way this will happen. Okay, it's very simple. You get your model, and remember, we added all of this gateway and all of that good stuff. So part of the gateway could be, whenever the model gets a request, part of the gateway could be just take that information, the input data that came in, and store it in a production database, right? In the database that contains all of the input data that came from the user. And then we can take that production data, which is real life data, and compare it to a reference data set. This reference data set is the data set that we use to train our model. And we compare it. There's going to be a monitoring process that's going to do the comparison and produce metrics and alerts. That's it. It's that simple. It's going to detect, oh, you know what? The production data contains more empty values or missing values than the reference data. And it will raise an alert, and you can act on that alert or not, or do whatever you want. Very, very simple to set up. Very, very important to track. Okay? It's that simple. Here is a parenthesis now that we're talking about input data and input features, because usually when you're, especially during the training process of your model, not the deployment, you already deployed the model, you're capturing data from production and whatnot, but usually the first step is for you to understand if your data has changed or not, especially during training. And people get sort of like scared about setting up a monitoring process and using Evidently, which is a new library. So here is a different way that you can think about this on how to solve this problem. This is a trick to understand whether two data sets, imagine your training data set and your production data set, have drifted. Okay? Very, very quick trick. Very nice to use this during an parenthesis. Very nice to use this during an interview because it lets you show off. People are like, oh, that's a nice trick. Okay, so this is the way it works. So imagine that you have your training data and you have your production data. Okay? There's no monitoring process. You're the savior who's coming in. You're not setting up a monitoring process. You're just helping the team explain and understand whether there has been any drift. So you get train data here, all of the features, multiple columns, and your label, whatever you are trying to predict. And you get production data, all of your features and your label, whatever you're trying to predict. First step, merge those two together. Create a new data set that adds all of the data coming from your train data set and all of the data coming from your production data set. So you create a single data set, putting all of it together. The difference is that you're going to drop the label. You don't care about the original label. You're going to create a new label, and that new label will be binary. And it's going to contain a 0 for all of the training data and a 1 for all of the production data, or vice versa. Doesn't matter. Basically, what you just created is a new data set for a binary classifier or binary classification model. Containing the label will indicate whether a sample comes from the training set or whether the sample comes from the production set. And you're going to just shuffle all of this crap. And now you're going to build that classifier. I call it adversarial classifier. Don't get fooled by the fancy name. This is just a binary classification model, whatever binary, a linear classification model, if you will. Decision tree, doesn't matter. It's a binary classifier. Your goal here is, or your challenge is, can you build a model with good accuracy? Can you build a model that determines, given a sample, that model should predict whether that sample comes from training or comes from production? Who can tell me what happens what means that if we can build that model, if that model is successful, what does that mean? What is the conclusion? Mark Smith.
You can build a model that, as described in the slides, predicts well, then there is distinct separation between your training data and production data. So that essentially means like drift has occurred.
Exactly. If you can tell by just looking at the input data that one sample comes from training and one sample comes from production, you're training with the wrong data, my friend. There has been distribution drift right there. Building that adversarial classifier is very simple. This is not like a whole entire process that you have to go through. Very simple. It either works or it doesn't. Your goal is for that adversarial classifier to not work. You don't want it to be good. If it's not good, that means that you cannot tell. If you cannot tell those samples apart, that's good. The data looks very similar, okay? If you can tell them apart, the data is different for some reason. Now, in real life, when you apply this to real life, what you're gonna find is sometimes you have pictures that give away where the data is coming from, and you might have not realized that. And it's not necessarily a problem because you might not be using those features, but let's say it's a consecutive ID, okay? Imagine that you have a consecutive ID as part of your data set, you know, where the training samples are 1, 2, 3, 4, 5, and then the production samples start in 1,000 or whatever. Well, if you include that number in this adversarial classifier, yeah, the adversarial classifier is going to do very well because it's going to quickly realize that every number starting from 1,000 going up is from production. So what you want to do when that happens is you're going to identify which one is the feature that's giving it away. So let's say when you go through this feature importance step that I have right here, see, so the adversarial classifier did very well. That means that the area under the curve, that's the AUC, the area under the curve. And if you are not exactly clear what that means that your classifier was great. It did very well. If it's much greater than 0.5, means it's doing very well. Then you're gonna go through a feature importance. So basically you're gonna compute which one is the feature that it's giving me that result. And probably the ID is gonna come out. Oh, it's the ID. The ID has the whole, the classifier doesn't care about anything else, just looking at the ID to make that determination. You're gonna remove that feature, remove it from your data set, meaning in this adversarial classifier, you're not gonna use it, just get rid of it and retry again until you get to 0.5. So this whole process will help you, number one, determine if there is drift, and number two, which feature is causing the drift, at least the most important feature that's causing the drift. So you can just do something about it to solve the problem. Again, this is not a replacement for monitoring, but is at some point, if you don't have a monitoring process, which happens to be very frequent, this is something that can get you out of that situation to understand what's going on, okay? It's very frequent that you have a company that's saying, I don't know why, but this is working fine in training. Why is it failing in production? Well, you do this. It's gonna take you a day doing this, probably now less time using Cloud Code or something, and you will determine if it's distribution problem. Okay, Mark.
Okay, I have seen something similar, and I would have your opinion on that. Instead of a binary classifier, we had deployed a clusterer, a hierarchical clusterer to be precise, and looked for every cluster if the distribution of the two labels from the training and the production data are quietly good mixed on that hierarchical data. We have the labels, of course, but we're
doing that on the labels. On the labels.
On the new labels. We also said, oh, does it come from the data set? Does it come from the training set? but we don't
Okay.
use a classifier, but it was a
Like
hierarchy.
a cluster and algorithm. I think it's the same idea. I will have to see the specifics, but it sounds to me right now when you're describing
Similar,
it,
yeah.
will achieve the same thing. Like those clusters will look fundamentally different.
What's the interesting part on that was we didn't know there are often feature combinations which make data different, not one feature. So when we identified our own cluster with only predominantly coming from the production set, we can look what combination of features make this different from the other one.
Yeah. That should also work. It sounds like it's very, very similar to this process here, for sure. Cool. All right. So with that trick, let's look now to operational metrics. This one is dear and near to my heart. I'm going to tell you an anecdote of why. So basically, this is what every DevOps has always done ever. So if you work on software, deploying systems, you should be doing this anyway. You're looking at latency and throughput, and you're looking at, are you utilizing the hardware? Like how much GPU and CPU are you using? How much memory you're using? You're basically looking at the hardware of the whole thing. Here's the anecdote. So I'm working for this Boston-based company. They're huge. And, I got brought in because they had a data science team, which is very frequent the way I got hired. Data science team in place. They built the model. The model is doing great in a Jupyter notebook. They have no idea what to do with that model. So got brought in. My job is to just deploy that model, make it useful. Okay, so how can we start using this model? So create an API, deploy it, monitor all of the freaking stuff. That was my job. Awesome. So I started working with them. Yeah, this is cool. The main challenge for them was how can we train this model with a humongous amount of data that they had. So just so you guys understand what they do today, they basically they have access to millions of job descriptions out there. Like every company that posts online a job description for a position, they basically scrape that and they get that job description. And the whole idea is to predict the expected salary for a given position in a given industry in a specific location. So they get paid a ton of money from companies who wants to hire, let's say this company wants to hire a team of electricians, and this company is in Connecticut, and they paid this company to tell them how much should we pay for electricians here in Connecticut. We have no idea. We've never hired electricians before. So, given a job description, they will predict in Connecticut what the price for that job position would be based on a bunch of data. So that was the model that they built. And they built the model. I did not build the model. So anyway, this is sort of like the pipeline that we had for them. So we built a pre-processing step, let's call it like that. And that pre-processing step would process those job descriptions and will extract information like the location where that job description was posted, the position, the industry, the experience of the person that they will hire in. And then we had a training process. And that's where the magic happened. And, when we train the model, when I deploy the model, or not deploy, when I deploy the training process, the pipeline who trained the model, it took about 18 to 20 hours to train the model. So it took a long time, right? Training time was a long time. And everything worked and everyone was happy and I was making money and, it's beautiful. And after a few weeks, few months after deploying this, obviously the next step was, okay, can we optimize the process now? Because we're spending a ton of money training our models. So we were in this process of how frequently we have to train, because it's 20 hours of training time. So is it justified to train every day or every month? Like 20 hours of GPU time, that's a ton of money. And I was assigned the task of optimizing the system. And I made the decision of using a 4 GPU computer to train our system. Just happened that our training or my training process was only using 1 GPU out of 4. So yes, 20 hours of using 1 freaking GPU. And I never realized that. So I was paying for 3 extra GPUs that my code was not utilizing. I discovered that when it was my turn to optimize the system. So basically that 20 hour could have been 6 hours only, not 20. I do not remember if I told them the truth that I had messed up. I do not remember if I came clean. I do remember that I optimized it from 20 hours down to 6 hours just by using what I was already paying for. The lesson here is I never freaking took 1 second of setting up a GPU chart showing me GPU utilization. I did not take a single second of doing this. If I would have done that, I would realize the very first day, after 1 minute of work, I would have realized that my GPU usage was never over 25%. That's it. It's that simple. Simple mistake that the company, not me, the company paid a lot of money because of it. All right, so your clue here is the process exists because it's important. And if you don't follow the process, if you don't follow best practices, they're going to come and bite you in the ass. It's that simple. So do what I say, not what I do. Okay? Monitor operational metrics. The third one is monitor prediction distributions. Mark Alexander, this goes back to the question that you asked. I do not understand exactly what label shift means. Well, prediction distributions will let you find out when you have label shift, when you're getting too many predictions of one type that you are not expecting. So for example, imagine that you get this, you get the first version of your model, or your model on day 1, you're expecting to see 2, 4, 6, 7 red predictions versus 3 blue predictions. And all of a sudden you start getting like 2 red predictions versus 8 blue predictions. This is just showing you different prediction distributions. It's not necessarily a problem, but you don't know that you have to check unless you realize that this is happening. So you should have Evidently, or any other tool in place, even if you build it yourself, that checks for, that alerts you if there are prediction distributions happening. Okay. All right. So that's the next one. Monitoring model performance. This is the one that everyone thinks when they talk about monitoring. Everyone immediately thinks about this one here, which is monitoring whether the performance of the model is going up or down. This is just one component. It's not the whole thing. If you only have this, great, but it's not the whole thing, obviously, whether it's so input and prediction distribution and whatnot. Here is you want to realize if the performance of your model is going down or not, right? And the way it works is very similar to the monitoring the input data, except now you need labels, because that's the only way you realize whether a prediction is correct or not. So there has to be a team in place taking a percentage of the predictions that a model makes and providing ground truth for those samples so you can actually compare them with what they should be. That's the only way you're able to predict whether your model is doing great or not. If you don't have those labelers doing that, you are screwed. You do not know if your model is doing great. This one here is very important. Does this make sense? Tools like Evidently will also help you, obviously, to doing this. You will see how to do this as part of the code walkthrough. I do that in the monitoring pipeline that I built. But the thing that you will not see in my code walkthrough is the labeling process. Instead, I created a pipeline that fakes the labeling process. You call it, and that will generate labels for the data, okay? Obviously, I'm not gonna ask you guys to just label penguin species. So I fake the labeling process. In a real application, you will need labels. you will need a team providing labels. Make sense? Cool. Final one, and then we enter into the last topic that we're gonna be, or the last two topics we're gonna be touching up today. Monitoring user feedback. This is what most companies do. However, they do it by vibes. Like somebody called me saying that this thing is not working correctly. Obviously, there are more formal ways of doing this. So basically, you don't look at your model, you don't look at the input data, you look at the results in the world, what's happening in the world. Let me give you just one example. Imagine that you have a recommendation model created by Netflix, and Netflix proposes all of these movies to you. If you guys have not watched Berlin, which is the first movie here, you should. It's a great, not movie, a TV show. You should definitely watch it. One of my favorite TV shows. So anyway, these are the recommendations by Netflix. And how do you understand whether those recommendations are good or not? How do you do that? Well, you can look at user feedback. How are people reacting to this movie? So for example, maybe you are tracking click-through rate, like how many times people are clicking on each one of those TV shows, and overall click-through rates going up, which is great. That's what you want to see. More people are clicking on those TV shows, but then watch time decreases over time. So yes, you are making something a little bit better, but then watch time, which is ultimately the metric that you care about, is just going down. So this model is drifting. I mean, whatever you're doing with that model is not working fine. Okay, so you have to check into that. That will be the last out of 5, the last recommendation that I have to monitor models in production. Any questions? Lucas.
Yes. So I wanted to bring up to the discussion the concept of feature store, because in order to monitor the input data and compare it production versus trained data, you need to have well organized the structure of the data with the dates according to the moment in which you train it.
Yeah.
So I guess my question is, does tools like SageMaker Feature Store different itself with a well-organized S3 structure bucket?
You're asking if something like SageMaker's Feature Store will organize the data properly?
Is there a difference between SageMaker Feature Store and a well-organized S3 bucket with?
I don't think so. So feature stores, so I have a love-hate relationship with feature stores.
Me too.
And the reason is they are an overcomplicated solution that work amazingly well when you have the need for that solution. If you do not have the need for a feature store, they're going to make your life way harder because they are very complex to use. So a feature store works well. Imagine you have like a huge company with a bunch of different teams, and those teams are building different models and using the central data set of the company in different ways. A feature store will let you store features, not just data. It's not a database where you just store data, that's raw data, but features. So we might have, okay, in order to create the age feature for our models, we're gonna process it this way. We're gonna use this specific method of imputation, and we're gonna standardize it like this, and we're gonna store the age feature in a feature store. So every single department across my company, they don't have to reinvent the wheel and go back to the raw data set. They can just read the age from the feature store. See what I'm saying? It's like you have like this intermediate step where features are going to make it into that intermediate step. And then everyone else is going to use the data coming from the feature store. That's awesome. That is not the type of I've worked for big companies like Dell, IBM, HP, Cisco. None of them are at that level, at least not in the teams that I worked on. They do not use features. They didn't used to use feature stores. At least, again, these companies are big, so they have like small teams. inside, none of them needed any of this. So I see these feature stores like a very complex problem. Again, I understand what they do. I do not recommend most people use them unless they have that very specific use case. Now, that's not answering your question. That's sidestepping your question. Your question is whether a feature store is well organized, is the same as a well-organized data set. The question is that a well-organized data set is well-organized. The feature store, you have to make it well-organized as well. You can screw up a feature store. There is nothing inherently organized about a feature store. You can make it messy. You can create it in a way that's going to help you do the monitoring process correctly. So does that make sense?
Yeah.
Like there is nothing special that's going to solve this problem for you if you use the feature store. At least I don't think so. Any other questions? Let me check. Actually, I have not checked the Q&A today. I don't know if there is anything in the Q&A today. There are some stuff. Okay, so curious if you've seen noticeable shifts. I'm going to leave that one to the end. Want to understand how this scenario is handled. Let's say Instagram uses personalized algorithm. User previously interested in X topic, and now he is interested in Y topic. How do they quickly identify this user behavior change and customize? So that's a great question. Basically, it happens to every single application that does this. The way it works is because Instagram or all of these social medias will frequently retrain using your data. So they will frequently retrain using your new behavior. And over time, your new behavior will overwrite your old behavior. You cannot react or have a knee-jerk reaction to me liking a post about an unrelated topic for my feed, and all of a sudden you're going to show me all of it about that. If you do that, the algorithm will be bad. So over time, what you have to find is the balance of how much should I show Santiago posts about watches versus guns. He was into guns before, but how quickly should that transition be? TikTok is famous because of their algorithm is really, really good. Like every person I've talked to, they say that TikTok algorithms shows them exactly what they want. I don't use TikTok, I don't know, but every person, my daughter tells me like, yeah, just try YouTube Shorts, Instagram, and TikTok, and she says that by far TikTok is the best, and by far YouTube is the worst, precisely because you watch a video one day about I don't know, like a little puppy, and all of a sudden your entire feed is puppies, and you're like, I don't care about puppies. You just freaking one video, and you're overriding everything that I care about. So you have to just find that balance, and it's like, how do you weight new data? And it's just a bunch of cool tricks that go into that just for your models to learn to react. Okay, so that's that one. In regression tasks, how is adversarial validation applied? It's the same, because it doesn't matter if it's regression or classification. You are not using the original label. So a regression problem is a regression problem because your target is a floating point value. It's just numeric, right? A classification problem, your target is categorical. You're not using that information. So if we go to the adversarial slide, which is this one here, notice that when I put together the training and the production data, I'm dropping the label. That label goes away. I'm not doing anything with that label. I'm creating a new label. Right here, it says drop original label and create a new label indicating if sample comes from train or tested. So it works the same if it's classification or regression, it doesn't matter. DJK, is there a common expectation for a business owner to understand or track why, how a model makes certain decisions per query transaction? So far, that's a great question. Is this something that is usually captured in some log? So, okay, so that is an amazing question. You probably don't remember, but as part of session 1, I think it was maybe session 2, we had a slide. There is one slide that talks about how to pick a good model, right? So 8 questions or 8 characteristics that you should consider in order to select your model. And one of those that I added to that slide is whether your model is a white box model or a black box model. In other words, interpretability, okay? Whether you can interpret the predictions that a model makes. So there are certain use cases where interpretability is a must. You cannot use machine learning unless you can explain the decision of the model, okay? So imagine that tomorrow we're gonna jail people based on the results of a model. So you input all of your data into a model and the crime you committed, and the model spits out how many years you're gonna spend in jail. Like, ain't gonna happen. The model there has to be a trace, a reasoning of, oh, you're going 25 years to jail because this and that and this and that, right? If it sounds like arbitrary, then it's just not gonna fly. So a model like that has to be white label. You should be able to trace it back, to trace a prediction back to the input data and explain it, right? Those are considered white box models because they are transparent. You can see how they think. Some other models, coincidentally, the better models, the best models that we have, the more powerful models, they are considered black box models because it's not easy for you to explain why the model made certain decisions. It's just not clear, right? Those obviously are very useful. And for many, many use cases, you do not need to understand that. But for the use cases where you need to understand what you cannot use. So is there an expectation? Not really. It's use case by use case basis. If I'm trying to predict whether I need to maintain a piece of equipment at a factory, the owner does not care about the explanation as long as the prediction is correct, because you can tell whether the prediction is correct or not. So the owner does not care about why is the model saying yes. If the answer is yes, you should, and the owner goes there and says, yeah, this is it's about to break, you don't care what is the reasoning process as long as the prediction is correct. But for certain use cases, you do need that. Mark.
Well, if your exact example, if the machine breaks, and why the machine breaks is not interesting for the business owner. That is true for exchanging the machine, but it's of course not true for the problem analysis and process improvement. So it might be even in that case that you would like to have a white box model, but if it's vastly worse than a black box model, you have to balance that. Do I need this data? Is that data valuable for my company? Other thing is safety applications. If someone has to go to jail, there must always be a reason. And if you kill people with a safety relevant software, then there should better be a good explanation why it's not your fault. And that is often also only possible with a white box model.
Yeah. So I want to be clear. Everyone wants white box models. We want interpretability. We just don't know how to get it, especially from these humongous large models. Forget about it. Like, we don't know. That's why precisely you get people thinking that these models are sentient and they think by themselves, and and other people say, no, that's just stupid. That's why the hype comes from. Have you realized that every time humans cannot explain something, we attribute it to something supernatural, right? Like before, like rain was because the gods were crying, and now we understand rain and we understand that that's not the way it is. But now these models work well and they're going to become AGI and they are sentient, and that's why Grok is. I see people fighting. Have you guys seen that? People fighting Grok like it's, dude, you're arguing with a machine. Are you stupid or what? Like Grok says, they ask a question and Grok says, oh, I think it's A, B, and C. And they're like, no, you're wrong. It's B and C and D. Like, you're arguing with a machine, just stupid dumb fuck. Jesus Christ.
I do that actually, but try to get it to tell the no matter the topic, the exact opposite things we post later. But this is a pastime play. And there are people that really think that this thing has anything.
Right. It's just numbers. It's literally, a bunch of matrix multiplications with some activation functions there. So anyway, so monitoring, great. I hope the next time you go to a company and you get hired and whatnot, you tell them, okay, when are we starting? When are we going to set up monitoring? Because it's really important. The next thing that I want to mention here is observability. Is just freaking important. And again, just big word, observability. What this means is you really need to have logs, metrics, and traces that you can just go back to debug your system. Okay. The phrase here is if monitoring tells you that something is wrong, observability tells you why that's wrong. Okay, so that's whole the idea. This is about being methodical and writing logs throughout your code. It's that simple. If you're a software developer, you should not be surprised about this because you should be doing this a lot anyway. Remember, a lot of machine learning people and data scientists, they don't come from a software development background. They missed all of these classes in the university. They did not take these classes in the university. So, yeah, 3 pillars: metrics for aggregated trends, logs for event details, and traces to map the entire journey, like every single request, where it went, what it did, all of that. Those are traces. I'm not going to get into the specific details. You have a slide here that explains or goes into details under metrics and logs and traces where they are. The point here that I want you guys to live with is observability takes your black box system and turns it into a glass box system or a white box system. That's what it does. Makes it more transparent. There is an analogy a long time ago, somebody very smart said, that he talked about it's like getting like a pen and making a pen transparent so you can see how much ink there is inside. And it makes a huge of a difference for a pen person if you can see how much ink you have left. You're never guessing. Just look at it and you know if you need to replace the cartridge, the thingy or not. So yeah, that's what observability is. And I'm gonna get into the last topic here. I really like this one here before we're done with the class. This is testing in production, and the reason I really like this is me coming from a software background. Every time somebody says, "Oh, I'm gonna test the application in production," I usually freak out. I'm like, "No, you're not supposed to test in production. You're supposed to test before it goes to production." However, I learned over time that this is not a problem. This is actually a feature. You want to be able to test in production because there are certain things that you can only learn in production. You cannot learn them while you're developing your system or building your model. Okay, so building your model and testing there, we call it evaluations. And before you deploy your model, we call those offline evaluations because your model is offline or your product is offline. So that's what we call it. When you hear, let's do offline evaluations, well, that it means everything like error analysis and everything that we did during session 3 and everything we talked about, back testing and all of that good stuff. Testing in production happens after I have my system online. Okay, so here is one example, just sort of like to motivate this idea. Again, it's a product recommendation system. Imagine that we built this beautiful website that this website sells products for people. So this section here of the website is going to list a bunch of products that the user can purchase. It's very simple. And then the user comes in and the user clicks on a product. Let's say they click on a desk picture, the product, which is a desk. And we have a recommendation model. A recommendation model, starts working at that point to recommend the user some related products based on the desk that they clicked on. Okay. And let's say a recommendation model comes out with a chair, a pen, a TV, a couch, a plant, and a microphone. Those are usually products that sort of like would exist in an office. The user clicked on a desk. So yeah, let's recommend office products. How do we know that those recommendations are correct? Who can tell me? How do we evaluate this model? How do you evaluate this model to understand whether those recommendations are good? I'm ignoring Mark here for a second, just to wait for anyone. Mark, like, just be honest. You just raise your hand before I ask the question. Doesn't matter. You're just going to answer it. Just be honest here. Birendere.
No worries.
Is the user clicking on what was recommended, like the way it was with the Netflix model? Is the user clicking on any of the recommended ones to go to that page and then see, or did the user buy it as part of the recommendation, and is it in the same part of checkout?
So that's how you evaluate it. You have to see, is the user, maybe the user clicking on a recommendation? Is the user buying ultimately one of the recommendations, right? That's how you evaluate the model. Notice that you cannot do that during development. You can't. So you are going to have a bunch of fancy metrics and a bunch of stupid shit during development that is going to sort of like tell you if the recommendations are kind of sure they are clustered within the same sort of like use case. Yeah, if I recommend a share after clicking on a desk, sort of like the share and the desk belong to the same cluster. That's the best you can do. But the ultimate test can only happen in production. So that's why testing in production is important, because if you don't have the ability to test that after you deploy the application, you really don't know what's going on. Jejan.
When you say in production, then you probably mean doing some kind of data analysis on the logs from the production in the SQL database or whatever database is used to store these user actions. So do you have like practical example on how would this system look like? Like how would this process look like?
Yes, I do. I'll get there in just a second.
All right.
There is Arun is saying here in the QA, do you also have to do A/B testing when deploying a new version in production online? I'm about to answer that question, Arun. So just wait for 10 more seconds and we'll get there. Mark, go ahead.
Why is that called testing and not just is success monitoring?
Because it's not just, like in this case, you might argue, well, this is just success monitoring. You'll see what in a second. There are multiple scenarios, and we're going to see what they mean in production. So let me give you the first one. Arun asked about this. This is A/B testing. A/B testing, everyone knows what it means. Anyway, here you're basically comparing two models in production. You're exposing these two models to a similar audience, and you are determining whether one model is better than the next one. So I want you to I want you to understand this scenario here. I have a system that's working, and I have version 1 of my model is already deployed there. Okay, that is my champion model. By champion, I mean the model that won the competition, version 1. It's there. It's serving users. But I created here a new version of that model. And offline looks very good. I run it through a bunch of test cases, and I back tested it, and all of that is looking good. Okay? You might decide, you know what, let's just deploy and cross our fingers. But that's risky. You don't want to do that because you might have missed something. So what is a better way of deploying this model? Well, you deploy it alongside the champion model. This version 2, that will be the candidate model. You deploy it alongside the champion model, and you slowly send some of the traffic to that new candidate model. and evaluate whether this candidate model is actually good or not. So over time, you're basically going to be getting more confident about this candidate model. Something important here, notice that it says 10% random, 90% random. That word random is very, very important. Who can tell me why you want to make sure that traffic that you're splitting is actually random? Legend.
Yeah, there's this canary release process where you want to just test your candidate model and see how it behaves, but also not disrupt the production, right?
We're going to talk about candidate release right after this one here. Now, in this one here, I'm going to tell you, when I get to candidate, I'm going to tell you what's different from A/B testing. But in this one here, why do you think it has to be random here?
This is like the statistical testing, the hypothesis testing that we do for A/B testing requires the samples to be random for the theory to hold.
But why?
Otherwise, it just, kind of introduces bias.
That is correct. So if you are not selecting the traffic that goes to the candidate model randomly, then you might be introducing bias. Therefore, you might not know what the results, if the results are really valuable. So let me give you one example. Imagine that we take every user of our application that's using the application from the mobile phone and send it to the candidate model. Because, mobile phone is usually like 10% anyway. So we're going to send every user from the mobile phone to the candidate model, and every other user from the website to the champion model. And the candidate model might be great, might be looking good, but you introduced another variable there. Maybe the users that are using your application from the mobile phone, there's something different about them. Maybe the use cases that they're trying to solve are less complex because they're using a phone anyway. So that would not be a valid comparison. For this to be a valid comparison, you need to make sure that both populations are exactly the same. Now, who can tell me disadvantages of A/B testing? What would be a problem with A/B testing? What would be advantages of A/B testing? Uday.
Well, I just wanted to comment on the random part.
Sure.
This is not my area of strength this entire class, session today, but I did work for a retailer, a very large retailer, and we quickly learned the word random doesn't mean what you think it is. It's extremely sophisticated to the point that the large retailer outsourced the word random to Adobe. And I think you made a very good example there. That randomness has to be some kind of uniform distribution, all fancy statistical words, trying to figure out how the users are. It was a very eye-opening experience, and how Adobe actually looks across your entire internet activity to determine if you're randomly here or over there. And so that's all I learned, but I did not learn enough to answer your second question. What's the bad disadvantages of A/B testing?
So disadvantages or advantages. So Paul.
So I think one potential disadvantage of A/B testing is that ultimately you may expose somebody to the lesser model of the two.
100%. 100%. Anyone else? Mark Smith.
Thinking to maintain infrastructure and inference, you might have a larger memory footprint if you have two models running in tandem, or some other resourcing issue or complexity that you introduce.
Yep, 100%. You're introducing complexity. You have to pay for more inference time because now you have two servers running two different models. DJK. DJ? Mark, Alexander?
I have a question lingering from the randomness. It's a little bit what Uday pointed out. And thing is, should we stratify here to make sure that the distribution for the both, not totally random, but stratified random?
It could be. Here is the challenge. What Uday says is it's very true and very important. The challenge is that if you have a different distribution going to the candidate model than you have to the champion model, that's going to be a problem. So if by random, what you do by random is just a
blind
simple,
random.
Every 10 requests that I get, one, I'm going to send it to the candidate model. Depending on your input distribution, you might be sending biased data to the candidate model. So yes, what Uday says is true. Random might not be as simple as just a function. Now, here's the other thing that I want to say. You've heard me saying it before. You always start with the simplest thing that could possibly work. And then if required, you add more complexity to it. So not like random might be random for 99% of the use cases out there, but there are certain use cases where just a random function is not going to give you a proper distribution for A/B testing to work. There are other scenarios, other testing in production scenarios that we're going to talk about that do not rely on that distribution to be random. You might want to look into them anyway. We'll get there in just a second.
Okay.
Mark Smith.
One other advantage, I don't know if anyone said it, but like you, by A/B testing, you dramatically reduce your risk if you're, slowly, incrementally, like rolling that out across like representative distributions of customers.
Yep. Vishwana?
Yeah, so disadvantage is that we have to wait for a certain sample size, and that might take a bit longer. And
Yes,
one
sir.
more thing is, I have actually worked with reinforcement learning techniques called as multi-arm bandits for A/B testing. So one of the main advantage over the traditional A/B testing is that when there are more branches, currently we just have 2 here. So let's say if we were to test 3 or 4 features, then this becomes increasingly complex.
Yeah. So Vishwanath said 2 things. One, I'm going to touch on in just a second when I show you the slide about disadvantages, which is really important. The second thing that he mentioned is that he's worked on multi-arm bandits. Multi-arm bandits, I decided to remove it from my list here of testing in production techniques. It's a valid testing in production techniques. Is also fairly sophisticated. Like he said, it gets really complex. Yes, fairly sophisticated. And most companies are not going to get to that point. Obviously, if you're working for big tech, if you're working for a company that has a massive size and scale, multi-arm bandit is just going to be a technique for you to consider, but very sophisticated for sure. DJK.
Hey,
Guys,
can
I
you hear me?
just realized, just 1 second, just a stupid mention here. I've taught this program for 3 years now, and I just realized right now in session number 5 that next to your hand up, it shows a little number that says the order of when you raised your hand. Okay, I just realized that. Okay, so now I see DJK is 1 and Caleb is 2, and it starts changing. I've been keeping track of it during this session. I'm like, wow, that's what it is. Jesus Christ. So I apologize if you saw me skipping anybody other than Mark Alexander. I've been doing that on purpose. But everyone else, I'm just, Jesus Christ, so stupid. PJ, sorry, go ahead.
Hey, no worries. Can you hear me?
Yeah, I can hear you.
Yeah, I was going to say, as one of the disadvantages, especially for large companies, I think A and B, there's so many changes coming to production. Probably it's very hard to pinpoint what's driving the behavior, right? Unless you really, really isolate it, then maybe it makes sense. Otherwise, you won't know like 20 different things coming in and impacting behavior, right? That's a disadvantage.
Yep. 100%. Caleb?
The big disadvantage problem is, so in your picture you have a model router, and if you do have a model router, it's easy to do random number, but like Uday was saying, kind of, this doesn't exist. There is no model router. There's things from the web, from apps, from different versions, from API. It never ever exists. And so I would think you're always going to be saying, I can't do random. The best I can do is find something to be an equal distribution on, like location or something. So that's what I would think happens. And then I was gonna say a huge advantage of doing this is once you set up two systems, you've accomplished a lot in terms of like deploying and rolling back and doing maybe 2 or 3, and that's going to get you so many advantages of these. So even just trying to do A/B testing will solve a lot of like deployment and problems like that.
Yep. Kevin?
I guess I'm wondering with A/B testing, would it, I guess I'm thinking like if you're on the critical path or something, sorry, let me rephrase my question. Is there a way to incorporate like user feedback? Like if you sort of, serve, model B, and is there a way to get feedback from the user to say like, no, like this is not at all what I wanted, and kind of incorporate that feedback? Or is that not good for A/B testing?
So it is, but it's, not for A/B testing. I think A/B testing, the focus of A/B testing is for you as the company who's producing these models to test these two models in the background. Users are never going to know which model is being used for which prediction. You could create a scenario where you do test different models by asking people, what do you think about this or about this? And I'm going to show you one of those right here, or one that's similar to that one here, which is going to be like what ChatGPT does. I don't know if that is very annoying to me, but so all of a sudden they show you two responses and they ask you, which one do you pick? Which one do you think is best? That would be that sort of like testing modality, where they're using users to tell them which of these two are the best answer. It's the best answer. I'm going to show you interleaving experiments in just a second, which is sort of like that, and that might help. All right, so like all you guys said already, number one, this limits the potential impact of mistakes. And that's why we do A/B testing in the first place. That's why you want to consider A/B testing. You want to reduce the potential mistakes of introducing a new model in production, okay? So unless what you're doing really doesn't matter, downtime is not a big thing, you should always consider doing a technique like this, okay? Like A/B testing. Obviously, it just provides direct comparison. Assuming that random is random for your use case, you are comparing two models. So you can easily tell, okay, so this model is actually better than this one here or not, okay? Some of the risks is that, number one, the impact is just for a small audience, but that small audience might potentially be getting a subpar experience. So if your model has a problem, if your model is not great, you are impacting at least some users. So that's still a downside. And I think it was Vishwanath, the one who mentions this, A/B testing takes a long time. It delays the cadence of deploying new versions by a lot. And the reason is because you need a lot of data for it to be statistically significant comparison. Like if you look at this, I'm only sending 10% of my data to the candidate model. You have to be running that model for a long, long time until you collect enough data to make a proper comparison. Okay, not just one day, but you need to run the model for a long, long time. Uday.
Yeah, I think that was the other point we learned very quickly. You need a statistician. If you're working for a large retailers, you're going to get a lot of data very quick because your website is so busy. But I think the key point we've been hearing from you, Santiago, is most of these problems, we have limited data, and limited data means you have to wait for a longer time to get more. Yeah, thank you.
Imagine that you are trying to roll out a model because you're seeing a distribution shift, but you're doing A/B testing, and you don't know whether your model is going to be good until 3, 4, 5 weeks from now, because that's when you can actually make a statistically valid comparison. So that huge delay is a downside, right? You just that 10% that you're sending or 5% that you're sending to the AB, to the second model, the candidate model, it causes a huge delay here. So that's one of the downsides. So then we have canary releases, and that it also comes from the software world. And I'm not gonna get too deep into this because it's extremely similar to A/B testing with one caveat. Notice that the percentage here now is targeted, not random anymore. So for candidate releases, the reason you run a candidate release is because you have a model and you want to ensure everything is working fine. You don't care about the quality of that model being better or worse than the champion model. You care about, is the pipeline working? Is my end-to-end system working? So what you do is you're gonna pick an audience as for a subpopulation of your user base, and you're gonna give them access to the new model, okay? In other words, usually free users you don't care about. That's what you do. Or whenever you see Apple saying, and our new system is going to be in, I don't know, this obscure country, available in this obscure what they're doing is canary releases, okay? They're sending their new system to an obscure continent or country. So who cares? That's what they do, okay? So that's what a candidate release is. You just deploy to that sub audience there just to ensure everything works, but those are not your most important customers because you are exposing them to an inferior model potentially. So you want to make sure if something fails, they are an inferior model, okay? So yeah, this limits the mistakes. That's the main advantage. If there is a bug in the pipeline, you are going to realize that that bug exists without exposing your most important customers to it. One of the potential, downside is that you don't want to compare. This does not help you comparing the quality of the models, okay? It does not, because the subset of your users is a biased population. You don't want to just compare the performance of the model there with the rest of your users. That would not be a valid comparison. You don't want to do that, okay? So let's go to my favorite one. My favorite one, the one that I've used the most, is this one here. It's called shadow deployments. And if your cloud provider is good, they will offer this out of the box, just like A/B testing. They usually offer the model router, they usually offer it. So shadow deployment is one of the best ones here, I think. And the whole idea with shadow deployment is that you are going to be deploying both models and making predictions with both models at the same time. But no user is going to be affected. So this is the way it's gonna work, okay? So you deploy the champion model. I mean, it's already deployed. You deploy your candidate model in the shadow, meaning you're gonna send 100% of all the requests to the shadow, to the candidate model, but you are never going to send those predictions back to the user. So the users will continue getting predictions coming from the champion model. But now you have a copy of those requests going to the shadow model or the candidate model, and you can evaluate how that model is doing in comparison with the champion model. Mark.
So this is like back-to-back testing in software.
What is that again?
In back-to-back testing, if you have two algorithms and let them run through the same tests and look which one performs when better.
I guess so, yeah. Yeah. That's the idea. So I have my new version of the model, and what I'm going to do is I'm going to say, you know what? I'm going to deploy it. I'm going to send the next week worth of data. I'm going to send it through both models. And at the end, I'm going to compute the performance of both models. And if mine is better than the previous one. There is no bias here involved. There is nothing like that involved because both models are getting exactly the same traffic. So there is a question there. Let me see. How do you, it's actually in the chat. Remember, guys, if I do not read the entire chat, so I'm going to answer this one here, Arun, but always remember to put the questions in the Q&A. How do you compare the results for shadow deployment? So what I'm comparing is I'm looking at the prediction of the shadow deployment, And I'm obviously, in order for you to compare these, you need labels. So I can compute how good the shadow the model did, and I can compute how good the official model did. And I can just one-to-one comparison right there. It's that easy. If the champion model is performing at 90% accuracy, and the candidate model, the shadow model, is performing at 92% accuracy, I know the candidate model is better. It's that simple. Anuradha.
So shadow deployments cannot work for LLMs.
Shadow deployments cannot work for LLMs. Why wouldn't they?
Because you are not sending the reply to the user, and you do not, you can't evaluate the response if it was.
Well, you are storing. So imagine an LLM is not. Imagine you're using an LLM to do some sort of like a summary of text. Okay, so let's imagine that that's what you're using the LLM. You can have the champion LLM. Let's say that's the OpenAI GPT-5. And you can be generating your summaries using GPT-5. And those are the summaries that you send to the user, okay? But you have a new version, GPT-6, internally, where you are also sending the query, generating a summary with that version. But that summary you're never going to send to the user. But you're going to evaluate that summary and compare it to the previous summary. And that evaluation process will determine which summary is better, right? Is it consistent? Does it, stick to the points? Is it too short, too long, too verbose, whatever it is? That evaluation can apply to the results. Make sense?
Got it.
Mare.
Yeah, hi. So I was trying to understand your previous example of recommender systems with this. So you would do conversion analysis to test the performance of the model in that case, but here you would not have any conversions for the shadow deployment.
Correct.
So
This shadow does not work for recommended systems.
Okay.
Because for a recommended system, the main signal is, do users like that recommendations? Do they act on it? And with shadow deployment, you are not showing the users the predictions of the shadow model. So this does not work for recommended systems. I'm about to show you the last of the testing in production strategies. That one is for recommended systems.
Okay.
Arun.
Hey, hi. So on the shadow model comparison part, right? So in A/B testing, it actually works because your user is interacting with the model, right? In this case, user is not interacting with the model. So just based on the answers or based on the responses, how would you know? So just imagine the old model give you result A and the new model is giving result B. How would you know the drift or basically the difference is better or worse? Wouldn't you have to actually test on the users at the end? Yeah.
So remember, this is not, so if your evaluation is based on what the user does, then this does not work. But not every model, you can evaluate model without understanding what users do with it. Imagine that you have a model that predicts whether a stock price is going to go up or down. You do not need user interacting with that prediction for you to understand whether the prediction is good or not. You just need to wait a second for the stock market to catch up and tell you whether the stock went up or down. And that's the information you use to evaluate whether the model made a right prediction or wrong prediction, right? Or you will have labelers or people who are going to look at the input data and provide ground truth. And then you can compare the ground truth from people with the prediction from the model and determine if those two match. If those two match, great. If they don't match, that was a mistake. And that's how you compute the accuracy. You do not need users to do that. You can do that yourself internally. Make sense?
Yeah, cool. Okay.
You Dave?
Sorry, I was on mute. Yeah, in the other screen that you had for the Canary, there was the 90 and 10, and the difference between the Canary and the shadow deployments in traditional software was the new solution, new version would never actually send data back to the end user. We would just use network layer tricks to never send the data back, but we would use other tricks to compare what the current production is doing versus what the new system is doing. We have to do all those tricks at that layer. I believe because when it comes to models, they're invariably an HTTP API. It becomes far more easier to put some proxies and do shadow much simpler. You don't have to need to know networking layer expertise for that. So is that how you've done it? Like what exactly?
I'm going to explain in a second how I do it. Just by the way, the whole idea with Canary is that users will see in Canary releases what we're doing machine learning. Here, you want users to see the output of a model. So because you want to test the whole end-to-end process, that's the goal of Canary. If you don't want your users to see the output of a model, because you're going to be testing that internally, then that's a shadow deployment, in which case you do not want to limit that to 10%. Users are not going to be seeing it anyway, so there is no point of limiting that to 10%. You will do the full 100%. And then analyzing internally how you do this. Now, how do you do shadow deployment? It's very simple. Like, number one, most cloud providers would do this for you. But the way it works is that you determine how much of the traffic you're going to send to both instances. And all of the input data that comes to the model is going to be saved. And all of the output data coming out of the model, the predictions, are going to be saved. That's it. That's the whole shadow thingy. Now it's your responsibility to go to that database. In the case of AWS, it's usually just a folder in S3 with JSON line files that get stored there with input data prediction. Input data prediction is now your responsibility to read that up and analyze it and determine what to do with that. That's it. It's just very simple. Mark.
If you run such a model and you might have problems with your champion model. So the customer gives feedback on the champion model. You could filter the queries of the candidate model if it at least improves and look at those specifically to at least see if the candidate model improves in the points where the customer was unhappy.
Right.
And for the rest, you could do a similarity measure to tell more or less automatically if the responses are quite similar to that, and then you would have
that's the whole idea here.
Approach.
This is like a flight simulator for pilots. Before they actually get on a plane, you put them on a flight simulator where they simulate like a real flight, an emission, and they do it all there. And you can evaluate them almost in the real scenario. Like a shadow deployment will be very real because you're getting exactly the same inputs. But that's what this is. If you fail, nothing happens. You don't die in a flight simulator. That's the beauty of it. If the candidate model fails, there's no harm because the user will not be exposed to this. And that's the main advantage of shadow deployment, is risk-free. Like, there is nothing that is going to prevent this from, like, if it fails, nobody will ever realize, okay? It also, it has the advantage over A/B testing that you don't have to wait for a long time. A/B testing, you're only sending a small percentage of data, therefore it's gonna take longer for you to have enough data to draw a conclusion. With shadow deployment, you do not need to wait that long because you're getting 100% of the data, okay? Main disadvantage, shadow deployment increases the load on your hardware, obviously. You are running every single inference twice. So you're spending more money to run shadow deployments. That might not be an issue for 99% of the use cases out there where everybody can afford like having two small models. It's a big issue if you have like a lot of let's say you're working with restrained hardware with the like on the edge, a robot or a camera with a very limited hardware. shadow deployment will be a big problem there because you don't have the GPU necessary to run or the CPU necessary to run. And obviously, shadow deployment, the other disadvantage is that your users, it's a curse and a blessing. Your users will never be able to provide feedback, okay? For the feedback part, if you're doing recommendation system, and these are my three last slides of this session, you want to do interleaving experiments. This is very popular. It's also fairly sophisticated. It's not easy to implement, but it's very popular. In fact, I think Google uses interleaving experiments for their main search product. So this is the way it works, okay? So imagine that I have my two models now, the champion model and the candidate model. And for every query that I get, I'm gonna send it to both models, okay? So imagine this is a product recommendation or Google search engine, which needs to provide a list of 10 results back to the user. So what I'm going to do here is I'm gonna get every one of the models to provide a response. Generate all of the recommendations, both models will generate recommendations, and then I'm going to interleave them, right? I'm gonna get some of the recommendations from model 1, some of the recommendations from model 2, and those are the recommendations that I'm going to send the user. So now I can track which recommendations the user likes. If over time, I detect that the user prefers recommendations from model 2, model 2 is gonna be the better model, and it's gonna stay here instead of me having to do this. Does that make sense? Very good at comparing two models, identical conditions. You are tracking user feedback, and you're exposing users to both models, and you're basically learning which recommendations the users prefer. Problem with this is that this is only limited for models that return a list of things, like, you know, a recommendation model or search engine or things like that. If you have a list of things, you can use interleaving experiments. The second problem is that it's sophisticated and it's not easy to implement. If you think about it, like, attribution is a big thing. You need to understand what attribution means. You also have to deal with the bias of which prediction should I put first. Should I put a prediction generated by model 1? Users will tend to click on that one more frequently than in the second one, so that will bias that. So how do you act against that? So it's more sophistication in order to implement this. But it works. And that is my last slide for today. So let's go to Q&A. Let me drink water first. What is everyone? Everyone, like, all of the cameras are off. Lucas, go ahead.
Hi, Santiago. So we have the training pipeline, we have the inference pipeline, and we have the monitoring pipeline.
Yeah.
So the monitoring pipeline is trigger every time you have an output from the inference pipeline, or is it a batch situation that triggers once a day?
Yeah, it really depends. It really depends on what you consider, what is part of that monitoring pipeline. Like in the one that I created, the monitoring pipeline, what it does is it does the input data, it monitors input data, and it monitors the predictions. It does the prediction, not only the metrics, but it's also the prediction distribution. It does not do, obviously, operational metrics, and it does not do user feedback. So when would you run those? Well, you can run them on a fixed schedule. I could compute those charts every hour or every day, and I could have those charts in front of my screen so I can be looking at them every day, monitoring how my models are doing, right? Not necessarily after every single request. Imagine that you have a model that receives 1,000 requests per day. Well, you don't want to regenerate that 1,000 times. You can regenerate that once a day or once every few hours. That's the way you will run that pipeline. That's what I've done before. Does that make sense?
Yeah, totally. And you also trigger some kind of a alert on it?
Yeah, so what you do with the monitoring pipeline, ideally, you will generate charts that will be accessible by the team without having to do anything. So that's number one thing. The second thing that you can do is you can generate an alert if you detect a problem that's more urgent to fix. Like, let me just give you an example. Imagine that you are tracking the performance of your model. Your model is going to go down in performance over time, and that's fine. But if you all of a sudden see a big gap, let's say a 5% gap between the accuracy of the previous time that I ran and the new time that I just run this, you see a 5% performance drop. At that point, you might want to generate an alert if you wanted to. I usually don't do that because those drops are very rare and usually you detect them before they happen, but you could do that. If you have a team that's looking at the charts, you really don't need to do the alerts. That's just, it sounds like it's like too critical. It's not. You can just looking at the charts, you're gonna get the entire picture. But you could generate the alerts if you wanted to.
Okay, but that's something that the library like evidently take care of it, or you
No,
need it in the
so
tool?
the library will give you the numbers. Now it's upon you to act on those numbers however you want to do that. The library computes the problems and it will tell you if there is drift. The library has formulas that you can adjust by the way that will tell you whether you want to consider this to be drift or not. Now, not all the drift can be treated equally. There is drift, and that drift might not be problematic, right? So that's what I'm saying. You need to determine what do you consider, like what type of drift I consider to be urgent and problematic enough for me to, let's say, send an email message, right? Or send a text message to somebody. But you have to do that. The library is only about computing the drift and telling you, hey, these are the numbers here.
Got it. Thank you.
Okay, so number one is Mark Smith.
I know you talked about like evidently, and we'll be using that like for other, just in terms of tooling for monitoring and observability. Like, do you have any thoughts on like Grafana and Prometheus? Like, I think those are like larger scaled systems like tooling, but like any thoughts on like between them?
No, I have not used them. I've used Evidently. I come from an AWS background, strong AWS background, where I've used a lot of SageMaker. SageMaker has their monitoring processes, which I've used extensively, and I hate with a strong passion. And when Evidently came out, Evidently is a YC-backed startup. They created the open source library, and they also have like a cloud service that you pay them and they do more stuff and store monitoring over time or whatnot. But anyway, when they came out, I was so freaking happy because SageMaker monitoring processes are just Jesus hard to use. Very, very hard to use. So those are the ones that I've used before.
Okay,
but
cool.
I know
Thanks.
there are many other libraries to do this type of stuff. Matt.
Yeah, maybe you partially answered this, but I'm trying to understand the chronology here. So how do we like practically handle retraining schedules or triggers to avoid drift issues, and then production tests, given that the new data keeps arriving and may make these tests quickly outdated?
Yeah, so that's a great question. Session 6 is going to answer that question. It's going to start talking about continual learning and retraining. I can give you like a quick answer to not spoil it too much, but basically there are different triggers for retraining. So think about them, like different use cases will require different things. The easiest one is just by frequency. What I mean by that is a schedule, not frequency. What I mean by that is you're going to retrain every day. That's it. That's your schedule. That's the best way, what I recommend 99% of people to do. But there is also ways to optimize that. Like, for example, by the volume of training data. You don't retrain every day because maybe every day you don't have new training data. So why would you retrain with the same data? So you wait to have certain amount of training data before you retrain. Or by drift, whenever your accuracy drops 5 points, now you're going to retrain. Or you do it by data drift Jesus, it's escaping me. Anyway, it's a bunch of different ways that you could think about when to kick off a retraining process. Those are going to be the triggers. It's up to you to determine based on your use case which one is going to be the best. But if you want my recommendation, 9 out of 10 times you want to do it on a schedule. That's the easiest way to do it. Lucas, go ahead. No, actually, hold on, Lucas. I'm skipping here. Anuradha, go ahead.
Yeah. So is there a use case where both the your shadow deployments and your interleaving experiments can be used, but you would prefer interleaving experiments?
So anything that I need to understand how users react to my predictions, it's going to have to be some sort of interleaving experiments. You're going to have to expose users and do the whole attribution of, oh, they clicked here, so I'm going to capture that click so I can later understand that they prefer that recommendation. So if you have recommendation systems, you want to do interleaving experiments. If you do not have recommendation systems, you can just use shadow deployment. That's the way I would think about it.
Okay.
Lucas.
So you talk about your helpful from AWS and SageMaker way of monitoring things. Is the equivalent of evidently on SageMaker is model monitoring, or is this a mix between model monitoring and feature store resource? Or
no, so evidently will be model monitoring. Yes, evidently doesn't do anything about feature stores. It's just evidently is a collection of classes that, given their data, the right data, it's capable of computing drift. It's capable of telling you, oh, this changed here. And they use a bunch of fancy formulas that are statistically, correct and whatnot. That's what evidently is about. It's just well organized, but you have to give it the data, and it does that. SageMaker, on the other hand, it's way complex to do because it requires to run processes that run inside Docker containers. And it's very, very finicky with the format of the data. The way you provide the format of the data is extremely finicky. And the way you configure where that data is stored is extremely finicky. So it's a lot of problems. I promise you, I think I spend like 90% of my time battling monitoring jobs with SageMaker instead of thinking of how to monitor this model better. It's just battling that they made a change, and now the format of the data, it was a number before, but now they're reading it as a string. So now I'm getting, I'm passing 1 as a string. This literally happened. And before, internally, they were converting that to a number. So 0, 1, 0, 1 numbers. Great. All of a sudden, they stop doing that, and now there are strings. So now I get all of these alerts about something. And it's just back and forth, and it's just... And then very hard to debug because they use Spark inside. The way they do the monitoring process and analyze all of the data is using Spark, and the logs are horrible, and you have to go through these processes and read the Spark log. I don't even want to remember that. It was just bad.
Yeah. Okay. Thank you.
Let me get a QA question here. Would you recommend a honeypot deploy testing in your regular CI/CD pipeline, or only if there is a security concerns? Can you remind me, DJK? I'm not a DevOps guy. What is a honeypot deploy testing? What is that?
Can you hear me?
Yeah.
Yeah, it's basically a special setup where you direct traffic to isolated site. So if somebody does hack in, they cannot pass that specific server. So you can still exercise, your security perimeter assessment, but the hackers, they think they're on the real system, but they cannot really propagate inside the network.
Gotcha. Yeah,
so it's a security aspect. Yeah.
It's a security best practice, very nice one. I think, yeah, this would be a great use case to study better.
So it sounds like it's more from LLM perspective, it's more like a need to know, it's like as need basis, right? Because this area is generally very...
I wouldn't do, I wouldn't do unless I have a reason to do this. Does that make sense?
Yeah, thank you.
Like it sounds complex and something that might be useful whenever you really have the need to do this. It's like if I have 3 users in my application, I'm not going to be doing A/B testing. I'm going to be deploying, but who cares with 3 users to my application? So all of these techniques and practices, they start making sense as you start getting serious about the things. But at the beginning, I wouldn't start with that. That's the way.
It was a general question because right now there's a lot of sensitivity around this area and there's a lot of competition and know-how. So that's one way to throttle this down. So that's what I was asking. Thank you.
Yeah. The next question here is, what kind of testing is it when ChatGPT gives you 2 responses and asks you which one do you prefer? Or is it just feedback collection and learning user preference? This is like feedback collection. It's like a simplified version of interleaving experiments where you have 2 models. And basically, what you're doing here behind the scenes is asking both models to provide 2 answers. And you're showing the user both answers. Instead of just showing the user one answer, you're showing the user both answers and asking them, which one do you prefer? And I hate it, very much hate it, because I don't have time to be testing for them. They're not paying me to test for them. So I always select the first one and just fuck you. That's what I do. But yeah, don't do that. Be nice and just read both answers and just start thinking about that and just tell them which one you prefer, because why not? But yeah, that's what it is. You're asking users which one you prefer. But some sort of interleaving experiments there. Can you talk more, find details about how you implemented shadow deployment in production? So the beauty of shadow deployments is that something like AWS does it by default. So you just have to say, I'm going to deploy, this is my champion model, and this is my shadow deployed model. And you deploy both models at the same time, and that's it. In fact, I think, let me see if that is true. Let me share my screen here. I might be doing that here in the code walkthrough, but I do not remember. So let's check it out here really, really quick. If I go to the deployment pipeline, I'm gonna make this a little bit bigger. But if I go to my deployment pipeline, oh, actually, no, you know what? It's there is a backend. I have a SageMaker backend here. This is the local. This is the SageMaker backend. So what do we have here? Load, label, deploy. Okay. Let's see if I'm doing it here. Okay, deployment configuration, not this. Get deployment. Okay, let me just go to that. No, this might not be here. I know I did it in the code walkthrough that use, oh, maybe here. No, no, I'm not doing it. I'm just creating a deployment, deployment configuration, flavor. There might be a function here. I don't know where it is. Okay, so I don't think I'm doing it here now. Sorry, just trying to. Okay, so I definitely did it when I had the SageMaker specific code. I had a chapter here to do shadow deployment, but okay, so what is the model add? Deployment model add to create a new production variant. Okay, so there is something here. You could extend deployment configuration with a mode parameter. Okay, so here is the mode parameter. There is a mode parameter. No, where is it? Okay, so might be something like this. I don't know, because this is, okay, so let me try to organize my thoughts here for a second. What I'm using here to do SageMaker deployments is the MLflow API wrapper that they have around SageMaker. So they have a wrapper that's specific for SageMaker, and that is what I'm using here in order to do deployments in SageMaker. The SageMaker SDK works a little bit different. When I had code walkthroughs for SageMaker, specific SageMaker code, you guys have access to those code walkthroughs. They're in the GitHub repo. I had an example of how to do shadow deployments. The way you do it is very easy. When you, at the time of deploying a model, you see this deployment model add, this will create a new production variant. Okay, so this creates a new production variant. Basically, when you have two variants, what that means is just a version. You have two variants side by side getting traffic. And then you can specify how you want the traffic to go. Notice that I added here, you can then route some of the traffic to the new variant using the SageMaker SDK. There is, I don't know where that is, but if I go here inside, I might get here, let me see. Yeah, I'm gonna have to check the API, the MLflow API, to understand where that is. But basically, let me just find replace here. No, no, yeah, I'm gonna have to check the API. I don't remember how it works specifically, but basically, in other words, at the time of deploying a model, you could say this model that I'm going to deploy is gonna be a copy. It's gonna be an added model, a new variant, and I want to route 100% of all of the traffic to both models, and that becomes a shadow model. In the UI of SageMaker, if you go into SageMaker and you go where the endpoints live, there literally is a section for shadow deployments, shadow models, and it's very easy to do. SageMaker takes care of the routing of the requests, takes care of saving the data coming out of the shadow models. It takes care of saving all of that data. So it's great from that point of view. You do not have to spend a ton of time trying to figure that out. That's basically the way it works. Okay, let me see. 2 more questions here. I have, actually, Lucas, go ahead.
It's about actually that I wanted to understand more about the box of model router and how it is materialized. This is a chunk of code. This is a step in a pipeline. It is a script running somewhere else.
Yeah, so in a cloud provider, that would be like a detail that happens behind the scenes, like you don't care. It's just something that happens. If you were to implement it from scratch, it will have to be the front end that receives, not the front end like a website, but the API that receives a request. That API does not answer at that point. Basically, it says, okay, which of the 2 models that I have, I'm gonna engage, right? That's what the router means. Is instead of just engaging all with the same model, you will have 2 versions and say, I'm gonna ask this model or this model, depending on a condition. But when you're deploying to a cloud like SageMaker, they take care of that. The models, you deploy them separately, and they have like the same interface. So like, for all that you care about, nothing is happening. You're sending a request to the same interface, but behind the scenes, they engage one model or the second model. That's what they do. Like a load balancer. A load balancer is basically a router that takes care of the load of each model in order to decide which model to engage. That's basically what it is.
Right. And the difference of being the first step in a pipeline that decides which way the data is going to be, you actually can materialize a model router in a first step in a pipeline.
Yeah, it could be. It's like the first thing, the first line of receiving that request. That first thing is going to be what's going to act as the router.
Thank you.
Okay, so I have one general question. If I want to create a model that needs to extract action items from some documents, would it be better to create an LLM from scratch or fine-tune an existing model which trained for some other purposes? Okay, so this here, basically, if I summarize it, is it better for me to use an LLM or to fine-tune an existing LLM to do something specific? The answer is it depends, but 9 out of 10 times, probably 99% of the time, you want to use an LLM from scratch because it's you want to use an LLM out of the box because that is the simplest possible solution. You do not want to get into fine-tuning unless you have to. Fine-tuning is an option is very expensive in terms of time and what you're going to have to pay to fine tune a model. And results are not guaranteed. You really have to know what you're doing. So my recommendation is always try to get as far as possible by just using the model out of the box. You have RAG techniques to augment the context of a model, use tools that augment the abilities of a model. Do all of that, consider all of that before fine tuning. Okay. Jajan.
One question. I was considering to parse PDFs using the model because the regex simply cannot extract all the information from PDFs. The PDFs are some bank statements, so would you then also say for this scenario that it's better to just train it from the scratch rather than use an existing model like a DeepSeek reasoning model and then fine-tune that one?
What do you want to extract from the PDF?
It's just some kind of the bank statements, like transactions are there, like row by row. But if you parse it, then it's all garbage, So it's not easy for a custom parser to extract the information in a meaningful way. Maybe it's possible, and it requires.
You want to use an LLM to do it? Is that what it is?
And then I tried it with an LLM, and of course, it's much more precise.
So use the LLM, but you're not fine tuning or doing it. You're using an LLM just out of the box, right? So my recommendation there is don't give the LLM the PDF and ask the LLM to solve it. And the reason is because LLMs are finicky when dealing with PDF documents. So a better solution could be taking the PDF document and turning that PDF document into text. There are libraries that respect even the positioning in text where the items are, like in a bank statement, you have a table with columns.
Yeah.
There are libraries that will turn that PDF with tables into tables in text, which is great because the order matters for a bank statement, right? Like if you reorder that, things are not going to mean the same. And then take that text and give it to an LLM. And just by doing that, you're going to get much better results. You don't have to train or fine tune an LLM to do that if it can solve it like this. Make sense?
Yeah, but I did try, like just one sentence there. I tried with DeepSeek. I think it's 14B version of the model, and it can run on my M1 Mac. And it's really bad performance compared to ChatGPT, when you give him the text, as you said.
You mean performance in terms of like a slow or the quality of the results?
The quality of response.
Okay, so it was worse DeepSeek, is that what you're saying?
Yeah. And it's a smaller model. It's a much smaller model. It's a much smaller model than ChatGPT.
Right.
And the question
is that's probably why it was worse than ChatGPT, right?
Yeah.
Because it's smaller, yeah.
So this is like the question which I encountered is like how to now find the best model to do this job, to be the cheapest.
Right.
I guess
because so now you are now looking at the trade-off. If you go with ChatGPT, you're gonna get great results, but it's more expensive than just using DeepSeek, which is faster, but it gives you worse results. So now you have to find in the middle what the actual answer is. Some people use this as some people explore the fine-tuning process to solve this challenge. Like maybe if they could fine-tune DeepSeek, they could solve the process here. My recommendation to you is fine-tuning DeepSeek, you have to take into account the man hours that's gonna take, right? The person hours that's gonna take to do. So yeah, maybe you're gonna spend 6 months fine-tuning DeepSeek, and after 6 months, if you would have spent that money on ChatGPT, that would have gave you like 10 years of runway. So just do the math. Fine-tuning is not a simple process. You need to understand what you're doing, and especially fine-tuning requires updates. So fine-tuning is not a done once and now my model is great. No, bank statements are going to keep evolving. So instead of instead of OpenAI updating their models, you are gonna need to update your DeepSeek model now with new bank statements over time. So again, it's just a trade-off. You're gonna have to find where the balance is.
Thanks.
Yeah. Okay, so let me go to next question here, and then I'm gonna go to Dinesh. The next question is, if I go through the full machine learning pipeline, EDA cleaning, feature engineering, preventing data leakage, training, testing with methods like invariance or back testing, then deployment and production testing, will the data still remain relevant by that stage? How long should this entire process usually take? Oh, yes. So if I understood correctly, the shelf life of data, it's not seconds, it's not, the shelf life of data stays relevant for days, it may be even months, maybe even years, depending on the problem that you're working on. So what you're saying here is that, like, if you build the pipeline to process all of this data, when you're done with the pipeline, the data is still going to be relevant. And even if you get new data, the steps that you're building are not tailored to specific. Maybe that's what your question is. I know you are still listening, so if you don't mind raising your hand and just talking this through, I just want to make sure
I'm just sorry. That's what I'm trying to understand. So maybe in some industries, the data is changing rapidly. So in that process, like by the time you get to that stage, I know there's you have retraining schedules, but you're still retraining, right? You're still then changing based on the new data. So by the time you get to that last stage, how do you make sure that it's still relevant, by that stage? So that's kind of.
So the actual values might not be relevant, but the decisions that you make, let's say you have to standardize your data. That decision, it's never going to go out of fashion, right? It's never going to change. You still need to standardize your data. You still need to handle missing values. By the time you finish your code, your pipeline, well, the actual data that you were using to train your model might not be relevant anymore because you already collected a bunch of other data, but the decisions that you made to build that pipeline will still be relevant. It doesn't change. Data is not going to change that much or that rapidly. That specific decisions, machine learning engineering decisions that you make are just you're gonna have to throw them out the window. It doesn't work like that, if that makes sense.
Right.
Does that?
So how long should that process usually take? Would it is there
Well, it really
a kind
depends
of
on the
number?
problem. It really depends on the problem. But you could have, if you give me a data set, by the end of the day, I could have a very simple pipeline ready to go. That doesn't mean that the pipeline will be 100% what it should be, but it means I should be able to start training a model by the end of today with no problem, to start exploring my data by the end of the day with no problem. So it doesn't take months of year of building in order for you to get to that phase, if that makes sense.
Yeah, I was thinking more of in a large company, you have to go through
doesn't matter.
so many processes.
So every large problem requires a bunch of small solutions stitched together. So not because a company is large, that means that to solve their problems requires a ton of time. That's just a fallacy. So if I go and work for a large company, guess what? They might be working with 1 billion samples. I only need 1,000 of them to train my first version of my model. I don't need the 1 billion samples. You know what I'm saying? Like, you need to start small. Nobody goes and tries to solve 1 billion sample problem at once. You need to understand that. You need to grow into that. So complexity has to be earned. Like the right to introduce complexity, you have to earn that by starting simple and then adding complexity to it. So it doesn't matter how big your company is. You're going to start by solving small problems and growing from there.
Okay. Cool.
Dinesh.
Hi, Santiago. Yeah, yeah. I got a little bit confused. When you say don't do the fine tuning of the model. So let's say I take the foundational model and then I give a 1,000 row CSV. So that is called a training, or is a fine tuning one?
It's a fine tuning process. You get a foundation model. You take 1,000 rows, a CSV with rows.
Yeah.
That goes through a fine-tuning process that sort of like adjusts how that model will behave. Yeah.
Okay. So basically, the code walkthrough, whatever we are doing, is a fine-tuning process. I just got like how to differentiate between training and the fine-tuning. Is both the same?
Okay, no, they're not the same. So training is when you have random, imagine your model like a set of numbers, okay? Those are the parameters of the model. So when I say that DeepSeek is 14B, that's 14 billion numbers, billion parameters. Those are all screw up. So they don't do anything. They start, we usually start them from random values. It's not necessarily random. They follow a distribution when we start, but they're meaningless.
Yeah.
And training is what goes through a bunch of data to adjust those values in a way that that model can actually make good predictions, right? So imagine that I use the model before training and I say, how much is 2 + 2? And the model is going to say Donald Trump as the answer. It's just nonsense. It's just nothing. It's not going to even say that. It's just blah, 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 random words.
Yeah.
Training will adjust those parameters, will set those parameters to the proper values, so the model starts behaving in a certain way. So when I say 2 + 2, the model says 4. That's how much it is, right? Fine-tuning is now you're going to get a smaller set of values, and you're going to sort of like, put some salt on this model, sparkle it a little bit with new samples so the model acts a little bit different. So a good way of fine-tuning a model would be take a model that before, when you gave it 2 + 2, answered with 4, and do it so it always answers with words instead of numbers. So it's going to say 2 + 2 equals the word 4. That is changing the behavior of the model. Still the same answer, but changing how the model answers. That would be fine. Go ahead.
In terms of like the code walkthrough, so whatever the process we are doing, so we took the foundation model and then we have some CSVs and we are loading. So that process, you call it as training or fine-tuning? That's what I was.
In our case, it is training, and I'm starting with the architecture of a model from scratch with no values.
Yeah.
So that what I'm doing is doing training.
Okay. So that's training. Yeah. So that's what I was.
Happens after you have a model that is useful. You fine-tune it to literally the words, the meaning of the words. Fine-tuning. It's just to make small changes to the model. That's what fine-tuning means.
Okay.
Makes sense? But the model already does something useful. You're just touching it a little bit. You're not retraining it, the whole model. Technically speaking, the way this works is imagine that you have a model with 10 layers.
Yeah.
So each layer contains multiple parameters.
Yeah.
Training will modify all of those layers. Okay? Fine-tuning only modifies certain layers, those near the output. And everything else is going to be frozen. So when you go to fine-tuning, you don't allow the model to relearn things. You freeze most of it and only adjust certain parameters. That's how fine-tuning.
Okay. And I also have like the general the terms which is used, like say that just like weights. What is that? Do we directly deal with weights, or we just give the data and it's the big array of values which in turn handles the weight? What is it exactly, the weights?
Great question. Let me try to explain it with a picture here. Okay, so let's try to explain it with this picture. Well, I have to share my screen here. Share my screen. Okay, let's try to go to this. Oops, agree and close, please. Jesus, what happened? Okay, you see my screen there? Okay, so this is one, well, this is actually more complex than what I want to show you. Okay, so imagine this is a neuron here. One parameter, one neuron of my network. A neural network is just a bunch of neurons.
Yeah.
A GPT-3, GPT-4, all of these models are just gigantic neural networks, right?
Yeah.
They have multiple neurons. Now, every neuron that you have, these here are going to be inputs. So these are X1, X2, X3, X4 or X5. Those are input values into your network. So if you're talking to ChatGPT and you're saying, who is the president of the United States? Each of those characters will be turned into a token, or each of those words will be turned into a token. Each token will be an input value. So maybe the first token, which is who, that is 123, that will be the input here. And the second token will be X2, etc. Now, each one of those inputs, which represents a neuron, will be connected to another input or to another neuron, and basically with a weight. So the connection of neurons will have weights in it. And if we look for neural network and we find an image, you will see something like this, okay? So let's go to that image. What is the image? You will see something like this. So you see all of those connections that are connecting the input layer.
We still see the data scientist website. Yeah.
Okay, so yeah, every one of those lines there, that is a weight. It's a connection from one neuron to the next, and there is a value associated with that connection. That is a weight. The weight is a parameter. When somebody says my model has 20 billion, is a 20B model, that means that there are 20 billion parameters, which is the combination of weights and biases. What is the bias? Well, when you look at the formula that's computed inside a neural network, basically the way it works is you take an input, you add it with a weight. So I take this input here, there is a weight associated here, and you add the input times the weight of every input connected to this neuron, and then at the end you add the bias, which is the value associated with the neuron. So that is just a formula. It's like a linear formula that you compute, and that's the way it works.
Okay, cool. Thank you.
I know this is a very hand-wavy explanation, but yeah, you deal with those parameters. Training sets those parameters. So training adjusts those weights. So every single one of those weight values at the beginning before training, they are nonsense. The training process sets those weights in a way where when you do a multiplication, given a set of inputs, you get the proper output value. All of those multiplications combined give you the proper value. That's what training means.
Okay, cool.
Make sense?
Yes.
If you really want to understand how this works, my recommendation is for you to start with a perceptron. If you start with a perceptron, this will help you understand at a very small scale how neural networks work. Okay. So the basic exercise here is, how can I set up a small neural network that knows how to do Boolean operations? So given a 0 and a 1, it does an AND. So my perceptron should be able to, if I show it a 1 and a 1, the output should be 1, because and 1 and 1 is 1. If I show it a 1 and a 0, the output should be 0. If I show it a 0 and a 1, the output should be 0. And if I show it a 0 and a 0, the output should be 0. So you should be able to set the weights for this one neuron network so it works. And now combining that will make like bigger neural networks.
Yeah, cool. Thank you.
Now, there is another question here that talks about the sigmoid. So what the heck is the sigmoid? Well, actually, I have a good TensorFlow playground. I have a good way to show you that. So look at this. This is a beautiful thingy here. What we have here is just a neural network. So let's take this neural network here. Let's for me to play. Okay, so here's the goal. Okay, here is the goal here. This is the data that we have. I want you guys to see that the data that we have has two classes, the orange class
Just a
and
second.
the blue class.
You're not sharing.
We are seeing the old screen. Yeah.
Oh, you guys are seeing the old screen. I apologize. Okay, so let's redo this. Let's go here. Okay, you guys seeing this now? No?
Yeah.
Okay, so I want you guys to see here, there is a blue class and there is a an orange class. Okay, this is the input data to a neural network. And this here is my neural network. Okay, so my neural network right now has two input values, x1 and x2. Okay, and given those two input values, I want to determine whether the class is blue or the class is orange. Jesus, what happens with this color? And I have a bunch of neurons. Okay, so this neural network is a classification neural network. It's going to classify whether a point belongs to orange or blue. Now here I can sort of like modify what I'm using, you know, the parameters of my network. So I'm going to run it like this. I'm going to run my neural network like this with these settings, and we can analyze the results. So I want you to see what just happened there. Do you see what just happened? Notice that the shadowed orange is properly dividing my two classes. Do you see that? So this means that this neural network is very, very good because it's properly able to separate both classes, the blue class from the orange class. Do you see, guys? You guys see that? I want to hear it. Yes, I see that.
Yes.
Yes. Okay, great. I did not use any activation here. So that means that there is no sigmoid being used. There is nothing. This is just straight algebra here, where I'm just multiplying the weights times the inputs plus the bias. That's all that's happening here. Nothing else. Because this problem is linearly separable, meaning a single line can tell these two classes apart, right? Just a single line. The neural network found that line, this white line that you see here, that properly separates the classes. But now let's go to a more complex problem like this one here. Or let's not make it that complex. Let's go to this problem here. Notice that there is no line that you can draw that's going to separate these two classes. Do you guys see that? There's no line here. It doesn't matter how you draw a line, it's not going to divide the blue from the orange. Do you guys see that?
Yeah.
Yep. Yeah. Okay. So if I use a linear activation, which means I have no activation function, nothing here, this neural network is not going to solve this problem. I'm going to prove it to you by clicking play. And I want you to see that is playing, is trying to find a solution. It's not going to find it. See how it's not finding it? So far, 700, 800 iterations, it has not found a solution. Because guess what? There is no line that's going to solve that problem. And algebra tells us that if we take a linear equation, it doesn't matter how many times we combine that linear equation, it's just going to give us at the end a linear equation. So if I say 2x plus y plus z, and I combine that with another 3x and another 4y, it doesn't matter how many times we combine it, we are going to get a linear expression at the end. And a linear expression is not going to be able to solve this problem. I can keep adding hidden layers. I can make this neural network amazingly big. It doesn't matter. This is not going to solve this problem. It's just not going to solve it. The only way, by the way, let me just show you here how it doesn't matter how big, how powerful I make my network, it's just not going to find that solution. Okay? So how do I solve this? Well, first of all, I don't need this many freaking neurons here. Just I can do it very simply. Actually, you're probably going to get like 3 neurons. And instead of using a linear neural network, I'm going to introduce what's called a nonlinearity, which is a function, an activation function that I'm going to apply, which, by the way, might not solve it. I might need to add a little bit more here. Hold on. And let's add here, why is not solving it?
Why? Why doesn't it solve it? Do you know?
It's not gonna solve it. But I need to introduce a nonlinearity in my activation function for it to actually find a solution. What a nonlinearity is going to do is going to break that linearity of an equation. It's a function that you applied to the result of, X times Y, meaning the inputs times the weights plus the bias. You compute that, and then you apply a function to it. In this case, I apply the ReLU function, which is a very, very simple function that basically takes anything that's negative, is going to turn it into 0, and anything that's positive is just going to stay positive. So if the result of your equation is a negative value, the ReLU function is going to set it to 0. And if it's positive, it's going to leave it alone. Sigmoid is another nonlinearity that basically it acts like a curve like this. Like if you're seeing a sigmoid function, it's going to look like something like this. So this is basically the way it's going to work. It's going to transform your linear equation into a nonlinear equation. Tanh is another one. You can try here different equations and see which one solves the problem. Sigmoid with this structure is not solving the problem. I have to try to see if there is a combination here where sigmoid would solve it. It might not solve it, but I don't think it's not going to solve it. Sigmoid is not going to be enough. But obviously, ReLU is. So by using ReLU, I immediately find a solution to this problem. Notice that now I have the blue part here, very concentrated, and everything else is going to be orange. And I don't need this big of a network. Like a smaller network is just going to do it just fine. Let me see. Yeah, just like this, you should be able to solve it. Yes, boom. And now you can keep trying different examples. That this example here, not good. I'm going to need more than that. Now, let's keep it like this. Let's see if I can add. Oops, sorry. There we go. Like adding an extra hidden layer solved the problem using ReLU. So again, you can play with this. This is going to give you an intuition of how these things work if you wanted to. You can change even the training data here, and you can change the noise and just get a bunch of different, cool examples here. Cool. Let me go back. Who raised? There's nobody with the hand up. There's a new question here. It says, if weights in the beginning are nonsense, should we put thought into it when training or just throw random things in there? So usually neural networks, the weights are nonsense, but the training process usually initialize them following like an algorithm. Like we have researched what are the best ways to initialize neural networks before training. So you don't have to worry about that. Whenever you create neural network, you can specify the way you want to initialize those weights, and your platform will do that for you. You don't have to worry about that. This is not a thing that you're going to have to spend too much time on it. How do we reconcile feature engineering and weights when training models, or are they not correlated? So not correlated. So weights are the parameters of the model. Those are the ones that your training process will transform. Feature engineering is the process for you to select which features you are going to use to change the weights of the model, to train the model. So basically, the way you think about this is the training process. We have a lot of documentation about it. Deep learning libraries know how to do the training process. You have to give them pictures. So what the engineer's job is usually not to worry about the weights and the biases. We know how that process works. The different architectures are going to change those values in different ways. Don't worry about it. Focus on the pictures here. What you do worry about it are how am I gonna, what is the structure of the network? Like I just did, solving the problem with sigmoid did not work, so I had to use a different activation function. So you have to select which activation function you would use. Then I complicated the data set, and having two hidden layers did not work. So I had to add a third hidden layer. Those are the decisions that you have to make as the person who's training a model. You usually don't worry about how those weights are going to be set or not, that the deep learning library will do that for you. Cool. Let me see. Does needing a more complex activation function hint at incomplete data normalization? I don't think so. I don't think there is a correlation there. Usually what works most of the time is ReLU. ReLU is probably activation function that you need. And unless you're doing like a binary classification, a binary classifier, sigmoid or tanh are gonna be enough. That's what you use for binary. For any other neural network, you're gonna use ReLU. In fact, if I go to my code walkthrough here, if I go to the code that you guys have access to the code walkthrough, we can go to the training. Let's just check the training file, and let's do, actually, this is in the common file because I reused that process. So here is my model, and notice that I'm using two different activation functions here. So this is the input layer of my neural network. This is a very simple model, obviously, for the Penguins data set. Then I have a hidden layer with 10 neurons. This is what that 10 means. A dense means fully connected. That means that every one of these 10 neurons is connected with every one of the inputs that come here. I think I have like 9 inputs. So there's gonna be a line for each one of those 9 inputs to the 10 neurons here. That's what dense means. It's a dense network. And the activation function for that layer is going to be ReLU, okay? Same thing happens with the next layer. I'm gonna have 8, and the activation function is gonna be ReLU as well. So again, what ReLU means is that the math operation will happen, and then the ReLU function is gonna set any negative values to 0, and it's gonna leave any positive values untouched. And just so you guys know, the person who came up with the ReLU had no idea that ReLU was gonna be so effective. He just used the ReLU. I recorded a video a long time ago about ReLU. The history of ReLU is fascinating, and everyone is surprised that it works so well. And then I have the final layer, the output layer of this network has 3 neurons only. The reason it has 3 neurons is because I have 3 classes. The species of a penguin, we have 3 different species. So I have 3 neurons, 1 for each species. And then I use a softmax. Can anybody tell me what a softmax does? Why am I using a softmax activation function here? Anyone who knows? So the softmax activation function, what it does is it makes sure that the sum of every value on that output layer sums to 1. So why do I want this? So imagine that I train my model, and I have, you guys are still looking at my screen. So imagine that I train my model and I get something like this. Can anybody tell me which class should I say is the answer? If I get this as my output layer, this is my output layer. So which class is the correct answer, the correct prediction here? Who can tell me? Shout it out because I don't see it. If you get this, there are 3 classes. This is class 0. This is class 1. And this is class number 2. So if I get this result, my neural network gets me this result. Obviously, class 2 is the highest value, isn't it? This is 0.91. So 0.91 is the higher signal than 0.7 or 0.8. So this tells me that the correct prediction is this one here. So I could not use a softmax function here, and I don't use any activation, and this will still work because I get enough signal here. However, softmax, by using softmax, what I'm asking is I'm taking these values and I'm squishing them in a way where the sum of them is equals to 1. So if I do a softmax of these 3 values here, I might get something that looks like this. Okay, this is just an example, obviously. So notice that the adding these up, it gives me 1, which allows me to say that with 70% confidence is the class number 2. So it sort of like lets me interpret the output here as a confidence level. So I can use that as a probability. 70% probability this value is correct, or confidence, not probability, but confidence. With 70% confidence, this value is correct. And 30% confidence is for the value not to be class number 2, but divided into class 0, class 1. And by me doing this, now this output becomes way more useful because I get the correct class and I get how confident my model is in that class. This is not the same as this. Like, obviously, here you don't know what the confidence is because these are just numbers. We call these logits. We don't know what those mean. It's higher. That's the only thing that we can tell, but we don't know how to interpret those. But by using softmax, I can now interpret them by saying, oh, actually 0.70, that's kind of like a confidence percentage. So that's why we use softmax in the output layer. It's very common that in every classification model, you guys are going to see that the output layer of the model uses a softmax activation function. And that's why you do that. Hopefully that makes sense. I know this is kind of like a little bit in the weeds. Like you start getting like here into the actual numbers, but that's sort of like the way it works. There is a comment here with classification systems. Have you tried always including a class unknown? Did it help? Not really. The reason is because it doesn't work as well as people think it will work. So that's not the way models work. So no, I do not use an unknown class. I've found most of the time that the unknown class is not useful. Here's the thing. For the unknown, let me try to explain from the beginning for the rest of the class. The whole idea here is that imagine that you're trying to classify, you have a classification system that's looking at pictures and you want to classify between 3 animals. And you have dogs, cats, and chickens. But obviously, the users might be sending you pictures of a lion, pictures of a wolf, pictures of a sheep, whatever. It would be great if we had, instead of 3 classes, you had 4 classes. And the whole idea with the 4th class is the unknown class. So your model would classify between dogs, cats, chicken, or unknown. That's the theory behind it. The problem is that what I found in practice is that that unknown class does not work as well as people think it will work. Because you really need to have a lot of data for that unknown class to become relevant. The way the model works is the model is going to look at an image and it's going to say, what does it look closer to? Does it look closer to a cat, to a dog, to a chicken, or to what? It doesn't work by saying, or if none, then unknown. That's not the way it works. It's going to compare it to patterns. So if the unknown category, you train it with a lot of lions, the unknown effectively becomes a lion. So when you get a picture of a wolf, you're comparing it against dogs, cats, chickens, and lions. And then you have a wolf. So it's not a lion. So it looks like a dog. It's going to classify the wolf as a dog. Do you know what I'm saying? Like your unknown category has to be all over the place for it to actually send some signal, which is not productive. So no, I usually do not use the unknown category. I do not find it helpful. Yeah, that's the sort of like the bottom line of this. Hopefully that explanation makes sense why the unknown class does not work in real life. What else? What else can I do to help? Just as a reminder, we have classes on Wednesday, we have office hours on Wednesday, and then we have the final class on Thursday. We're going to be talking about agents and MCP and A2A and continual learning on our last session. But of course, not because it's our last live session, that means that we're done. You guys have access to everything in the community. I'm going to keep bringing sample codes. And the next cohort is going to be in November, which all of you are obviously can participate. You don't have to tell me. You don't have to send me a message. You don't have to ask for permission. You just need to show up. That's it. Yeah, so depending on your use case, Christopher, you might get that unknown class to work. But the important thing here is to remember what the model is actually doing. The model is not discriminating and saying, oh, if it's not these 3, then it's unknown. That's not what's happening. The model is comparing with 4 categories now, assuming that you have 3 classes and 1 unknown. And as long as the model finds that what you just got is similar to the 4th category, then the model is going to add it there. And then it's going to look like it works. But think about what will happen when you have classes that do not look at that unknown. It's not going to get classified in that unknown. It's going to get classified in the one that looks the most similar to that class, not in the unknown just because it's not any of the other 3. Yeah. I think now the point is to take a real world problem and solve it within the framework from the ML School code. That would be my recommendation. I know many of you have done that already, or many of the students that have gone through the program have taken this template and have tried to apply the template into their companies. Maybe they were training a model or they had something in production and they basically took the template and say, I'm going to replace it with my own model. Even if you do not have a real life example, you don't have to have a real life example to practice. You can get the template that I have and replace the Penguins model. Throw it away. Find a new model that you want to build and build it on top of this thing and try to understand what this thing is doing. I've gotten very good questions on Discord from people that the only reason for them to be asking those questions is because they are getting into the weeds. Like somebody yesterday found a problem with the code. So his question was, why are you doing this? Doesn't make sense. Yeah, you're right. That was my mistake. And the only way you could have found that is because you got deep into this and analyzed the code and realized this dude is just made a mistake here. Okay. Doing that is going to give you more than anything, more than lessons, YouTube videos, all of that is crap. Doing the thing is what actually teaches you. Yeah, what else? Anything else I can do to help? All good? Cool, awesome. So then I guess I'll see you guys on Wednesday.
Thank you, Santiago.
Santiago. Bye
Thanks,
bye.
Santiago. Hey, guys.
Thank you.
Yes.
Bye-bye.